Hey dreamers, and welcome to the Sleepy Voyager. If you enjoy calm, thoughtful documentaries that help you drift off wiser than you woke up, please tap subscribe and the bell. It helps the channel a ton, and it means you'll never miss our next sleepy journey through the cosmos. A new object shows up in survey images as a tiny moving dot. At first it looks like noise or a camera glitch. Scientists compare pictures from different times. The dot shifts in a straight, steady way that stars do not. That means it is real and nearby in space, not a background star. The Discovery system logs it and gives it a temporary label. After more checks, it receives a formal name, 3I Atlas, which means it is the third interstellar object found, and it was first spotted by the Atlas survey. Interstellar means it does not come from our solar system. It is just passing through from the space between stars. We can tell because its path is not a closed oval around the Sun. The math shows a hyperbolic orbit. That is a path that bends near the Sun and then keeps going back out forever. Its speed is higher than typical comets or asteroids that belong to our solar system. Even after the Sun's gravity slows it a little, it is still fast enough to escape. Right after Discovery, telescopes around the world point at it. Observatories in different countries take turns because night moves around the Earth. More images make a track of dots. Computers fit a curve to this track to define the orbit. Each new night reduces the uncertainty. Early data can be shaky, so getting follow-up quickly is important. Teams share measurements through public systems so everyone can refine the numbers together. Brightness tells us about size and surface. The object is very faint. That means it is either small, dark, far away, or all three. By measuring how its brightness changes as it rotates, scientists can estimate its spin period. If the light goes up and down on a schedule, that suggests an uneven shape or surface patches with different reflectivity. A big swing in brightness hints at a stretched or lumpy body. A small swing suggests a rounder object or a surface that reflects light more evenly. Colour gives chemistry clues. Astronomers record brightness through different filters such as G, R, and I. Comparing these tells whether the surface is more like rock, ice, or dusty organics. If the colour is redder, it might have space-weathered material like many distant small bodies. If it looks neutral, it could be fresher rock or ice. Spectra, when possible, split the light into many narrow colours and can reveal gases or specific minerals, but 3I Atlas may be too faint for detailed spectra in small telescopes. Activity is checked in every image. If there is a fuzzy glow around the dot, a coma, or a short tail, that suggests ices are warming and turning into gas, dragging dust off the surface. Some interstellar visitors act like comets. Others look inactive and more like asteroids. Whether 3I Atlas is active depends on how close to the Sun it goes and what it is made of. Photometry teams compare the object's size in pixels to nearby stars to see if it looks puffier than a point. Risk is measured in a calm, methodical way. Scientists project the orbit forward and backward with uncertainties. They check for any chance of a close pass with Earth. Scales like Torino and Palermo help communicate risk, but for interstellar objects a simple statement works. Does the path come near Earth or not? With more data, the error bars shrink and the answer becomes clear. In nearly all cases, interstellar objects are just fast flybys with no hazard. Because it is interstellar, its speed and angle make planning slightly different. It moves across the sky faster than many known comets. Observers need accurate coordinates updated often. Exposure times must balance faintness and motion to avoid streaks. Some telescopes track at the object's rate so it stays sharp while stars trail. Others take short exposures and stack them in software to boost the signal without blurring. Time matters. Interstellar visitors brighten for a short window near their closest approach to the Sun and to Earth, then they fade. Teams schedule dense observing campaigns during this window. They request spectra on big telescopes if the weather and brightness allow. They also try radar if the object passes close enough, but that is rare. Most information comes from careful visible and infrared light measurements. Data handling is straightforward. Observers calibrate images to remove camera effects. They measure the object's position against background stars whose locations are well known. They report the positions and brightness to central databases. Orbit fitters recompute the trajectory and publish updates. Anyone can see the revised orbit diagrams and plan new observations. The process repeats day after day until the useful observing season ends. Rotation and stability are checked for safety in science. If the light curve shows an extremely fast spin, that can suggest a strong monolithic body. A slower spin could point to a rubble pile held together by weak gravity. If the brightness pattern changes over weeks, it might mean the object has jets of gas or is tumbling in a complex way. None of this implies danger on its own, it just builds a clearer physical picture. Simple comparisons help people understand scale. A typical small interstellar object could be tens to hundreds of meters across if it is dark, or smaller if it is very reflective. At interstellar speeds, even small sizes correspond to large energies, which is why scientists always check orbits with care. But space is huge, and exact hit geometry is extremely unlikely. The main goal is to learn, not to alarm. Naming and archiving follow standard rules. The 3I tag marks it as the third interstellar object after 1I/Oumuamua and 2I/Borisov. Atlas credits the survey that found it. Future papers will cite these names so results stay connected. If dust or gas is detected, those details will be added to catalogues. If not, it will be listed as inactive. Either way, it joins a small but growing group that helps us compare objects made around other stars to the ones we know. Public communication keeps things clear. Scientists try to avoid dramatic language. They explain that interstellar means interesting and rare, not automatically dangerous. They show the orbit plot, the brightness curves, and the observation schedule. They say what they know, what they do not know yet, and what they expect to learn next. This steady approach helps everyone follow along without worry. In the background, models run on computers. These models test many possible shapes, spins, and surface types to see which match the data. They also explore different origin stories, like being ejected from a young planetary system by a giant planet, or being chipped off during a collision long ago. The best-fitting models are kept, the rest are set aside. Over time, a simple database story takes shape that anyone can understand. As the days pass, the object moves on. It gets a little brighter, reaches a maximum, then dims. Observers hand off from one hemisphere to the other to keep coverage steady. The orbit solution becomes stable enough that even small telescopes and schools can find it using shared coordinates. People take one more set of measurements before it fades below reach. The files are saved, the plots are updated, and the object continues into deep space, while the information stays here for everyone to use. We find faint moving objects by taking many short pictures of the same patch of sky and asking a simple question: what changed? Wide-field survey telescopes like Atlas scan strip after strip each night, making a quilt of overlapping images. Software subtracts a clean reference image, built from many earlier clear nights, from tonight's fresh exposure. Anything that wasn't there before stands out as a little dot of leftover light in the difference image. Most leftovers are junk: airplane flashes, thin clouds, cosmic rays, a hot pixel. A few are real and repeatable. Those are the ones we keep. Because stars sit essentially still over minutes, the trick is to watch for motion. The system takes images of the same field several times in a night with a fixed cadence. For example, every 10 to 20 minutes. It then compares the candidate dots frame to frame. If a dot lands where simple straight-line motion predicts, it earns a detection. 3 or more detections spaced in time form a tracklet, a short arc on the sky that says, this point of light is moving in a consistent way. Tracklets are the basic building blocks of discovery. Raw detections are noisy, so we filter ruthlessly. First-pass filters reject shapes that are too fat or too sharp compared to the point spread function, since real objects should look like tiny star-like points under the night seeing conditions. Brightness thresholds remove spurious blips near the detection limit that don't repeat. A machine learning classifier trained on thousands of labelled examples scores each candidate by how real it looks, and low-scoring artifacts are dropped. What survives is a small list of plausible movers. Those tracklets are linked across the night and across many nights. The software searches for compatible speed and direction, building longer arcs called tracks. A track that spans multiple nights is far more useful because it pins down the curvature caused by the sun's gravity. With curvature, a first-guess orbit can be fit, and that fit predicts where to look next. Predictions produce fresh images, fresh detections refine the orbit, and the loop tightens until the uncertainty shrinks from a wide smear to a tidy ellipse on tomorrow's star chart. Cadence is everything. If you wait too long between images, a fast object will leap too far and you'll miss the link. If you observe too often, you waste time and cover less sky. Surveys choose a cadence that balances speed and depth. 2 to 4 revisits per field per night, then repeat on the following nights. The telescope's limiting magnitude, how faint it can see in a short exposure, sets the smallest and farthest objects it can catch. Better seeing and darker skies push the limit deeper. Moonlight and haze pull it back. Difference imaging would be easy if the night sky were a static backdrop, but it is alive with motion that mimics targets. Satellites leave streaks, planes blink, wind shakes the dome, thin cirrus makes stars breathe brighter and dimmer. The pipeline learns to ignore straight streaks, applies masks around bright star halos, and uses stationary source vetoes so a real star that twinkles doesn't get flagged as new. Even so, human reviewers or automated broker systems still glance at the top candidates to catch weird failure modes the code didn't expect. Precision astrometry is the quiet hero behind all of this. Each image is calibrated against catalogues of star positions so that a single pixel step corresponds to a known offset in right ascension and declination. This lets us measure positions to fractions of an arcsecond, which is like spotting a coin from kilometers away. Photometry, how bright the object is, gets calibrated too, using standard stars in the field to correct for atmospheric effects. Good astrometry fixes where an object is going. Good photometry hints at what it might be. Once a candidate survives the pipeline, its measurements are reported to a central clearinghouse, such as the Minor Planet Center. Other observatories can see the provisional positions and jump in for follow-up. Follow-up is the lifeline of small, fast, or interstellar objects. It stretches the arc, reduces the orbital uncertainty, and prevents lost objects. Small telescopes contribute time series photometry to catch rotation. Larger ones try spectra. Networks in both hemispheres pass the baton as the Earth turns so the coverage barely sleeps. Sometimes a target is so faint and fast that single exposures show nothing obvious. In those cases, we track and stack. Using a predicted sky motion, software shifts each image so the moving object lines up perfectly, then stacks them. The object adds up into a sharp point while the stars smear into short trails. This raises the signal without blurring the target, like whispering the same word into a recorder and then playing all the whispers together until the word becomes clear. If the prediction is slightly off, we search a small grid of rates and directions until the point pops out. Non-sidereal tracking is the hardware version of the same idea. Instead of letting the telescope follow the fixed stars, we drive it at the object's own speed and direction so the target stays pinpoint and the stars streak. This demands accurate rates and steady mounts, but it preserves more light from very faint objects, allowing shorter exposures and better time coverage. For rapidly changing targets, that time resolution can reveal flickers from rotation or small bursts of activity that stacking would smear away. Discoveries don't happen in a vacuum. Weather and the moon write the schedule. Bright moon raises the sky background and washes out faint dots, so surveys plan around lunar phases, or switch filters to wavelengths less affected by moonlight. Thin clouds scatter light and create gradients that confuse subtraction. Wind limits how fast the dome can slew and how long you can expose without shaking. Even the temperature of camera electronics matters, since warmer sensors grow noisier. Every night's log quietly records these realities so later analysts know why the detection threshold moved. False positives are a fact of life, and we learn from them. A pattern of repeated discoveries near a bright star may signal a reflection ghost. A cluster of moving dots along a satellite track is often a rolling shutter artifact. A sudden burst of new sources across the whole frame usually points to a calibration problem. Each lesson becomes a new rule in the pipeline, lowering the burden on human eyes and freeing more time for true sky changes. Over months, the false positive rate falls and the discovery rate climbs. For rare interstellar candidates, a few extra checks kick in. The pipeline tests whether the fitted orbit is unbound, eccentricity greater than 1, and whether the object's inbound speed remains high even after accounting for measurement errors and non-gravitational nudges, like outgassing. If those conditions persist across multiple nights and multiple telescopes, confidence grows. Teams then request faster turnarounds and deeper exposures because interstellar targets move on quickly and fade, and missed nights are hard to make up. Communication turns a handful of photons into shared knowledge. Alerts are posted with machine-readable formats so robotic telescopes can react automatically. Observers share finder charts with updated ephemerides, noting hazards like crowded starfields that make subtraction tricky. If the target shows signs of activity, teams coordinate filter choices so colours and gas lines are covered without duplication. When a night fails due to weather, someone else often has clear skies and fills the gap. The global handoff becomes as important as any single mirror. In the end, the method is simple but disciplined. Scan wide, revisit often, subtract yesterday from today, link moving dots into arcs, fit an orbit, predict forward, observe again, and repeat. Each loop reduces uncertainty, each night adds depth, and each shared measurement lets the whole network see more than any one telescope can. This is how we find things that don't want to be found. By turning the changing sky into a steady rhythm, listening for the faint beat of a traveller moving against the quiet choir of the stars. An interstellar object is any natural body, usually a small one like a comet or asteroid, that does not belong to the Sun's family and is simply passing through. We recognise it by its path and speed. Solar system objects move on closed loops around the Sun, circles and ellipses. An interstellar object follows an open path, a hyperbola, which bends around the Sun and never closes. The key number is the orbital eccentricity. If it is greater than 1, the orbit is unbound. Another helpful number is the excess velocity at infinity, often called V infinity. Even far from the Sun, after gravity has had its chance to slow it down, the object still carries a leftover speed that is not zero. That is the signature of a visitor from outside. Two early examples set the pattern. The first was labelled 1I/Oumuamua, discovered in 2017, and the second was 2I/Borisov in 2019. The I stands for interstellar. Oumuamua behaved like a small inactive body with unusual brightness changes and a slight non-gravitational acceleration. 2I/Borisov looked like a more typical comet with a coma and tail, outgassing detectable in many filters. Those two cases taught observers what to expect and how fast they needed to react, because interstellar visitors move quickly across the sky and are observable for only weeks to a few months at useful brightness. How do we tell whether a new discovery is interstellar? First, position measurements from several nights are used to fit a preliminary orbit. If the eccentricity is clearly above 1 and stays there as more data arrive, confidence rises. Second, the object's speed inbound, measured relative to the Sun, is compared to the escape speed at that distance. If it exceeds escape speed with room to spare, it cannot be bound. Finally, we check whether small effects like outgassing could fake an unbound solution. If the answer is no, we accept the interstellar classification. Once confirmed, the object receives an I designation with an index and a discoverer tag, for example, 3I/ATLAS, if ATLAS found it. Composition and appearance vary, and that variety is part of the lesson. Some interstellar objects will act like comets. Ices warm near the sun, gas escapes, dust rides along, and a coma and tail appear. Others may remain inert, reflecting sunlight without obvious activity. Photometry, the careful tracking of brightness over time, can hint at shape and spin. A large brightness swing suggests an elongated form or contrasting surface patches. Colour measurements through standard filters tell us whether the surface is neutral, reddish, or something in between, which loosely connects to rock, organics, or ice. If the object is bright enough for spectroscopy, observers can look for gas lines like CN, C2, or OH and reflectance slopes across the visible and near-infrared to refine material guesses. Many interstellar targets, however, are so faint that we rely on broadband colours and light curves rather than detailed spectra. Speeds matter for both science and logistics. Typical inbound speeds relative to the Sun are tens of kilometres per second. That means the object crosses the sky quickly, changing position by many arc minutes from night to night. Observers need accurate, frequently updated coordinates, ephemeridese, and they may switch their mounts to non-sidereal tracking, driving the telescope at the object's own rate so the target stays sharp while stars trail. Exposure times must be short enough to avoid smearing, or images must be track and stacked in software to align on the moving point before summing. Because the observing window is brief, coordination across longitudes and hemispheres helps fill gaps caused by daylight, weather, or the moon. Non-gravitational forces can play a role. When ices sublimate, they act like tiny thrusters, pushing gently on the nucleus and adding a small acceleration that pure gravity models do not include. Radiation pressure from sunlight can also nudge very low-mass dust or porous fragments. These effects are small but measurable if the astrometry is precise. In practice, orbit fitters test models with and without such accelerations and keep the one that matches the data best. The presence of a non-gravitational term does not change whether the orbit is bound or unbound by itself. It mostly fine-tunes the predicted path across the sky. Where do these visitors come from? The leading idea is ejection from young planetary systems. In a new system, planetesimals, building blocks of planets, scatter off growing giant planets. Many are tossed inward and destroyed. Many are tossed outward, where a fraction exceed the escape speed of their star. Close stellar passes and crowded birth clusters and interactions with binary stars raise the ejection rate. Over millions of years, a galaxy's worth of systems can seed interstellar space with vast numbers of small bodies. Most wander in the dark forever. A tiny fraction cross the Sun's neighbourhood and become visible to our surveys. How common are they? Early estimates based on the first detection suggested that there could be a huge population passing through the solar system all the time, mostly too faint for us to notice. The measured rate depends on how deep and wide our surveys are. As survey sensitivity improves, the expected discovery rate rises. Upcoming facilities with larger mirrors and wider fields will push to fainter magnitudes and should reveal smaller or more distant interstellar objects more often. Even with better instruments, each detection remains rare enough to trigger intense time-critical follow-up. Sizes are difficult to pin down because brightness depends on both size and reflectivity, albedo. A dark surface reflects little light, making a large object look small. A bright, icy surface reflects more, making a small object look bigger. Researchers estimate sizes by assuming a plausible albedo range based on colours and behaviour. For inactive bodies, thermal infrared data can help separate size from albedo by measuring heat emission in addition to reflected light. For active comets, dust production complicates the picture because the coma adds light that is not from the solid nucleus alone. The difference between an interstellar object and interstellar dust is scale. Tiny dust grains from outside the solar system have been measured directly by spacecraft and indirectly by their effects on starlight. They are common and flow through the heliosphere. Macroscopic interstellar objects, the kind we can track like Oumuamua or Borisov, are much larger and rarer. They are massive enough to hold shapes, spin, and sometimes outgas. and they are individually discoverable by optical surveys. Capture is theoretically possible but unlikely. To trap an interstellar object into a bound orbit around the Sun, its energy must be reduced, usually by a three-body interaction or by strong drag forces. In practice, most visitors fly through on fast, shallow arcs because nothing in the inner solar system provides the sustained drag needed to bind them. Planets like Jupiter can deflect paths significantly and even temporarily hold objects, but permanent capture without a fine-tuned sequence is rare. This is why almost all confirmed interstellar trajectories are open hyperbolas rather than long, looping ellipses. Observing geometry shapes what we can learn. If the object stays at small solar elongations, too close to the Sun in the sky, we cannot point most telescopes at it safely. If it rises high at night at a favourable phase angle, we get better signal and better shape information from its light curve. The best windows often happen before or after closest approach to the Sun, when the object is bright enough and well placed in dark sky. Because these windows are short, alert systems share coordinates quickly so that many sites can contribute data while conditions are good. Risk assessment for interstellar objects uses the same CALM tools applied to native asteroids and comets. Propagate the orbit forward with uncertainties, look for close approaches to Earth, and update as new measurements arrive. Inbound speeds are high, which means the object spends little time near Earth's orbit plane, reducing opportunities for close passes. The vast majority of interstellar detections have no practical hazard. The focus remains scientific. Learn about materials and processes in other planetary systems by sampling the small bodies they have shed. Naming follows a straightforward rule so records stay organised. The integer before the I counts interstellar discoveries in order. The tag after the slash credits the survey or discoverer. This system parallels the way comets and asteroids are catalogued, but keeps interstellar visitors in their own list because their dynamics and histories are different. As observations accumulate, databases store positions, brightness measurements, colours and spectra so that later studies can compare objects, search for patterns, and test formation and ejection models. Finally, it is useful to set expectations. Most interstellar objects we find will be faint, fast, and brief in our telescopes. Many will offer only light curves and rough colours. A few will be kind enough to show comas, tails, or measurable spectra. Each one still adds a data point to a larger picture. How often other stars make comets and asteroids, how those bodies age in interstellar space, what surface materials survive long journeys, and how our detection methods can be improved. With every confirmed case, the 101 becomes a little more complete, and the next discovery becomes a little easier to understand and observe well. A path through space is not just a line, it is a set of numbers that tell you where a body will be, and how sure you are about that prediction. When a new object appears, the first thing scientists ask is how the path sits with respect to the Sun and the plane where most planets live. They look at the orbital inclination to see whether the object moves mostly in the ecliptic like a typical asteroid, at a steep tilt like a long-period comet, or even retrograde, meaning it goes the opposite way around the Sun compared with the planets. High inclination and retrograde motion often mean unusual dynamical histories, and for a fast newcomer they can immediately explain why the track on the sky looks wrong to a trained eye. The next flag is the shape of the path itself. A bound body has an ellipse with eccentricity less than 1. An interstellar body shows a hyperbola with eccentricity greater than 1 and a non-zero excess speed at infinity. That single parameter, excess speed, instantly changes the way the rest of the analysis is done, because it says the object will not loop back for a second chance. To turn telescope measurements into a path, we fit an orbit. The fit begins with positions on the sky, right ascension and declination, collected over hours to days. With only a few points, many orbits can fit the same dots, as scientists speak of an admissible region, a cloud of possibilities rather than a single answer. Two tools help shrink that cloud quickly. The first is high-precision astrometry tied to modern star catalogues, which reduces systematic errors in each position. The second is time baseline. adnites on each end of the arc and curvature appears, letting gravity reveal its signature bend. For very short arcs, analysts use systematic ranging, which sweeps through distance and radial velocity combinations consistent with the measurements and throws away the ones that are dynamically impossible. The surviving set gives a first picture of what inclinations, speeds, and closest approach distances are even plausible. Uncertainty is never a guess. It is calculated and carried forward. When an orbit is fit, the software also builds a covariance matrix, a compact way of describing ellipses of uncertainty in all 6 orbital elements. Propagating the orbit to a future date means propagating that covariance too, which turns a point prediction into a probability footprint. On the sky, that footprint is often called the line of variation, a narrow path where additional observations are most valuable. Observers point along that line to collapse the uncertainty further. The result is not just a better position tomorrow, it is a safer and simpler answer to the question everyone asks in plain language: how close does it come? Close in dynamics has a specific measure called the minimum orbit intersection distance, or MOID. It is the smallest possible distance between the object's path and Earth's path, ignoring the timing. A small MOID does not mean a collision, it means the lanes cross. You still need both bodies in the same place at the same time, and fast interstellar objects spend very little time in any one lane. Even so, a small MOID tells scientists to keep a close eye on timing uncertainties as they shrink. For interstellar visitors that sweep through at tens of kilometers per second relative to Earth, the brief crossing time typically makes any real intersection unlikely, but unlikely becomes ruled out only after the fits stabilize. Another set of angles matters for whether we see the object well. The argument of perihelion and the longitude of the ascending node tell where the object crosses the solar system's plane and where its closest approach to the Sun occurs. Combine those with the inclination and you learn whether the object approaches from high latitudes, whether it dives through the inner system near Earth's orbit, or whether it stays mostly outside the plane where observing geometry is harder. If perihelion occurs while the object is near the Sun in our sky, small solar elongation, observations become difficult or impossible for safety reasons. If perihelion is offset from the Sun in the sky, the observing window is better, and we can sample the curve of its path more evenly. At planetary scales, gravity does more than curve paths, it can focus them. Gravitational focusing means a slow object experiences more effective target size for a planet because the planet's gravity pulls it inward, increasing the collision cross-section. Interstellar visitors arrive fast, which reduces focusing so the effective target grows far less. This is one reason high inbound speed lowers practical impact probabilities even when a projected line on a plot looks alarmingly close. For objects that do have low relative speed, gravitational focusing increases the need for careful modelling of close approaches and so-called keyholes, tiny regions in the plane of a flyby that, if crossed, set up a resonant return years later. Interstellar objects do not have resonant returns, so keyhole mapping is largely a native asteroid problem, not a visitor problem. To describe a close approach precisely, analysts use the B-plane, a geometric plane perpendicular to the incoming velocity of the object relative to a planet. Imagine throwing a pebble past a sphere and drawing a plane just upstream of the sphere. Where the trajectory pierces that plane defines how the flyby will bend. The orbit and its covariance are mapped into the B-plane coordinates, producing an uncertainty ellipse. If that ellipse lies far from the planet's centre, the encounter is safely distant. If it touches or overlaps the small circle corresponding to the planet's radius plus atmosphere, further observations are urgent. Interstellar speeds squeeze encounter times to hours, but the same B-plane logic applies. Most ellipses stay well clear. Non-gravitational forces are checked as a second-order effect. Outgassing can act like a tiny thruster, and radiation pressure can nudge small or very porous bodies. For active comets, analysts add parameters to the orbit model that represent a gentle push aligned with the Sun and adjust them to match the data. If those extra parameters significantly reduce residuals, the small differences between measured and predicted positions, they are kept. If not, they are left out to avoid overfitting. Including or excluding these terms can shift a close past prediction by thousands of kilometers over weeks, so the decision rests on whether the astrometric scatter truly demands it. Retrograde and high inclination trajectories deserve special attention because they change encounter geometry and relative speed. A retrograde approach increases the closing speed with Earth, shortening the observing window and making the object streak faster across the detector. It also shifts the phase angles at which we see the object, altering how brightness depends on geometry and complicating size estimates. High inclination paths cross Earth's orbit at steep angles at the nodes. Timing tolerances are tighter, so one more night of data can move a predicted closest approach distance dramatically. This is why alerts for unusual inclinations tend to include requests for rapid follow-up, even if the early MOID is not small. All of this rests on the quality of the inputs. Star catalogues set the reference frame. Better catalogues reduce systematic offsets that masquerade as orbital curvature. Weather logs explain outliers. Windy or thin cloud frames are often down-weighted or rejected. Telescope tracking rates need to match the object's motion. Small errors smear the point and bias the centroid, which feeds directly into the orbit. Pipelines increasingly use robust statistics that resist outliers, so one bad image does not steer the fit. Teams run Monte Carlo clones, thousands of orbits sampled from the covariance, to explore the full space of possibilities rather than trusting a single best-fit line. When the fitted path has settled, the result is a compact set of orbital elements with uncertainties plus easy-to-read products. Sky maps with confidence corridors, tables of closest approach distances and times, and brightness forecasts under different phase angles. Observers use these to plan exposures and filters. Educators use simplified diagrams to show why small changes in angle and speed translate into big differences in future positions. Decision makers, when they need to, use the same numbers to calibrate language. A routine flyby, a noteworthy but harmless close pass, or a case that merits extra monitoring. For interstellar visitors, routine usually wins, but the path that makes scientists sit up is the one whose geometry and uncertainties are interesting enough to teach us something new, while remaining clear enough to communicate with everyday words and simple plots so anyone at any age can follow along without fear. When scientists talk about a worst case, they are not trying to scare anyone. They're building a box around the most extreme, physically plausible outcome, so they can check whether safety margins, plans, and tools are good enough. The point is to define, quantify, and practice, not to predict doom. Every worst case begins with 3 ingredients: how big the object might be, how fast it could be moving when it reaches us, and where and at what angle it could arrive. Those feed into the simple physics, kinetic energy scales with the square of speed and with mass, and then into more detailed questions such as whether the object would break up in the air, explode as an airburst, reach the ground as fragments, or hit the ocean and push a large amount of water. Each branch has different effects and different playbooks. A practical worst case is never a single number. It is a family of outcomes traced across uncertainty bands. Early after discovery, the orbit has wide error bars, and the set of possible futures includes paths that pass far away and paths that come closer. Analysts propagate thousands of clones of the orbit forward, each slightly different but consistent with measurements, and ask what fraction enters a small space around Earth at the same time Earth is there. If the fraction is effectively 0, there is no case to worry about. If it is not 0 but very small, they watch how that fraction changes as the new data come in. The change matters more than the snapshot. Risk should fall as measurements improve. If it temporarily rises because an uncertainty ellipse shrinks in an unlucky direction, teams prioritize fresh observations to resolve it. A worst case is only taken seriously if it remains in play after careful updates. not because of a single early fuzzy calculation. There are two kinds of uncertainty to manage. Aleatory uncertainty is the natural randomness in things like how an object might fragment. You cannot remove it, you can only account for it. Epistemic uncertainty is missing knowledge. Unknown size, unknown composition, unknown spin that shrinks with more and better data. Worst-case planning focuses on the second type first. Gather colours, light curves, maybe spectra, and radar if geometry allows to pin down size, reflectivity, and shape. Even a simple brightness curve can separate a small shiny object from a large dark one, a difference that changes energy estimates by orders of magnitude. As knowledge improves, the worst becomes narrower and usually less dramatic, because the unknowns that once forced conservative assumptions are replaced with measurements. Impact effects split naturally by altitude. If the object is small or fragile, the atmosphere does most of the work. Friction and pressure tear it apart, and the energy releases high in the sky as an airburst. That produces a bright flash, shockwaves, and sometimes window damage over a region, but no crater. If the object is stronger or larger, some mass can survive to low altitudes or the ground, creating a blast wave, seismic shaking, and ejecta close to the site. Over water, a shallow angle entry at high speed can produce a strong airburst with less risk of a large wave. A vertical deep water impact of a substantial body is a rarer case that can drive a significant local or regional tsunami. Worst-case analysis maps these branches with simple conservative inputs so emergency planners can see boundaries. Which sizes are strictly an airburst problem, which sizes demand local evacuation, and which would require regional actions. Speed and angle control much of the hazard. A steep, fast entry compresses air more violently and drives breakup lower, strengthening the surface shock. A shallow entry spreads energy over a longer path, reducing peak overpressures, but widening the footprint. For interstellar visitors, inbound speeds are generally higher than for typical solar system impactors, which increases energy but also shortens the time the object spends near Earth's orbital lane, making the odds of being in the same place at the same time much lower. Worst-case tables therefore keep the speed variable explicit rather than assuming a single value. Planners then ask conditional questions. If an unlikely high-speed, high-mass case remained after weeks of observation, what are the safe actions and timelines? Communication norms are part of the plan. A worst case is always presented alongside the most likely case, and a best case with clear language that says what is known, what is assumed, and what would change the picture. Scales exist to help with this translation, but for rare visitors, a plain sentence often works better. Here is the current chance of a close pass, here is the size range, here is what we would do if new data lifted that chance above a threshold. Thresholds are chosen in advance to avoid emotional decision-making under pressure. They look like this. If the probability of impact exceeds a small value, and the potential energy implies at least local damage, then trigger round-the-clock tracking. If it exceeds another value within a fixed horizon, convene civil protection and space agencies to discuss mitigation or evacuation planning. If deflection is still on the table, lock down launch and mission timelines based on ready-to-fly hardware. Deflection belongs in the toolbox, but it is bounded by time. Slow push methods, gravity tractors, or sustained propulsion need years. A kinetic impactor needs months to years of lead time to launch, navigate, and hit the target. Late detection turns the plan towards civil protection on the ground rather than space hardware. Worst-case drills therefore include two branches, a space mission available branch and a no time for space mission branch. The second focuses on impact point refinement, public guidance, and practical steps such as moving people out of a narrow corridor days in advance if a small but non-zero probability remains. Drills also include false alarm and stand-down practice because a responsible system must be able to say clearly and publicly that new data removed the need for action. Material properties matter, so worst cases are parameterized by strength and porosity as well as size. A monolithic stony body couples energy to the air and ground differently than a porous icy aggregate. Models test strong, medium, and weak cases to bracket outcomes. The same is done for fragmentation, one piece versus many pieces. Multiple fragments spread energy and risk, often lowering peak damage but widening the area. These knobs are kept visible in planning documents so that if a late spectrum suggests volatile ices, or a light curve hints at a contact binary, the scenario can shift smoothly without rewriting the whole plan. Geography is not an afterthought. A worst case over uninhabited land has different priorities than one near a city. Over the ocean, the question is not just wave height, but which coastlines are within reach, how much time exists to issue targeted notices to mariners and coastal communities, and whether existing tsunami warning networks can handle an impact source instead of an earthquake source. Over high latitudes, communication and logistics challenges shape evacuation routes. Worst-case binders include maps, rerouting plans for air traffic, and checklists that translate orbital updates into ground actions like moving assets out of a predicted overpressure contour. Governance and roles are defined before any alert. Scientific networks detect, measure, and refine orbits. Coordinating bodies share updates across countries. Civil authorities own decisions about people and infrastructure. Private operators, satellites, airlines, utilities receive tailored technical advisories. A well-run worst-case exercise makes sure the handoffs between these groups are smooth, that contact points are current, and that messages are consistent. The exercise also tests surge capacity. Can observatories add nights on short notice? Can computational centers absorb rapid reprocessing demands? Can public information channels deliver calm, repeatable messages in multiple languages? An important discipline in worst-case thinking is value of information. Before asking for a costly observation or a major public action, teams ask what decision the new information would change. If an extra night of astrometry could shrink the impact corridor by half, it is worth it. If a challenging spectrum would not alter any decision, because the size range already guarantees only an airburst, it can wait. This prevents busy work and keeps attention on the steps that reduce real risk or real uncertainty. It also reduces the chance of confirmation hunting, where teams chase measurements that only strengthen what they already believe. There is also the problem of crying wolf, which worst-case planning must address head-on. The solution is transparency and cadence. Updates arrive on a predictable schedule with the same fields every time: date, geometry, size range, probability, next steps, so that changes stand out against a steady background. When a scenario falls off the table, the update explains why. New measurements shifted the path, or a refined size estimate moved the energy below a concern threshold. When a scenario persists, the update states exactly what would retire it, and when the next chance to do so will occur. This rhythm builds trust and prevents the vacuum that rumour likes to fill. Finally, the mindset matters. Worst cases are not prophecies. They are stress tests. They keep instruments sharp, data flows clean, and decision lines short. Most of the time, the outcome is pleasantly boring. Better measurements show a harmless flyby, models go back on the shelf, and the after-action notes improve the next drill. On the rare day when a risk survives scrutiny, the entire system, from telescopes to town halls, has already rehearsed who calls whom, what gets said, and which switches get flipped. That is what worst case really means in this context. Not a guarantee of bad news, but a commitment to be ready, with numbers, with options, and with simple, honest words everyone can understand. Measuring danger starts with writing down what we know, what we think we know, and what we still need to find out, and then using the same yardsticks every time so numbers mean the same thing from one object to the next. The first yardsticks people hear about are the Torino scale and the Palermo scale. The Torino scale runs from 0 to 10 and is meant for the public. 0 means no risk at all or nothing unusual. Most new objects live at 0. A 1 means normal discovery, a very small chance of an impact that will almost certainly go away as more data come in. Levels 2 to 4 mean the object deserves attention and more observations, but no special action. Levels 5 to 7 would mean a genuinely threatening situation that needs a planning and possibly mission design. Levels 8 to 10 would mean a certain collision at different energy levels, getting worse as the number rises. In practice, almost everything you hear about stays at 0 or 1 and then drops to 0. The Palermo scale is for experts and uses a logarithmic number to compare the impact probability of a specific object to the average background chance of impacts of the same size over the same time window. Negative Palermo numbers mean less risky than the normal background. 0 means equal to background. Positive numbers mean more risky than background. Most flag cases sit far below 0 and then disappear with better data. Behind these scales are simple ingredients. We need an estimate of size, an estimate of of speed, an estimate of where the object could be in the future, and the probability attached to that future. Size and speed tell us energy. Position and timing tell us whether the object and Earth can be in the same spot at the same time. Energy is usually expressed two ways: joules, which are the physics units, and megatons of TNT, which are easier to picture. The conversion is fixed. 1 megaton of TNT corresponds to a large number of joules, so even small rocky bodies carry a lot of energy at cosmic speeds. But energy alone is not destiny. The atmosphere absorbs and redistributes a great deal of it, especially for smaller or weaker bodies. So we also ask how high breakup would happen and whether the result would be an airburst or ground impact. The probability part comes from orbit fitting and uncertainty. Every new measurement makes the predicted path sharper, but early on the prediction is a smear, not a point. Analysts create many clones of the orbit by sampling within the current uncertainties and then project them forward. If none of the clones hit Earth, the probability is 0 at that level of knowledge. If a few pass through Earth's position at the right time, you get small probability. That number can go up or down with new data. The healthy sign is that the confidence intervals shrink. When probability dips below a preset very small threshold, the case falls off alert lists. When it rises above a preset threshold for a defined time window and the energy level, follow-up observation becomes urgent. The thresholds are published in advance so everyone knows the rules. To keep things steady, risk is always reported with the same set of fields. A standard line includes the object's designation, the observing arc length, the current best fit orbit, the range of sizes consistent with the brightness, the nominal closest approach distance and time, the impact probability over a defined window, and the two scale values. A note explains the main driver of uncertainty, usually lack of length in the arc, sometimes the possibility of non-gravitational forces like outgassing. A second note says exactly what observation would change the picture the most. One more night from this longitude, a spectrum to constrain albedo, or radar ranging, if geometry allows. This keeps attention on information that moves the needle instead of noisy details. Communication is as important as calculation. A calm update rhythm helps everyone. Instead of blasting news whenever a number twitches, teams post at regular intervals unless something significant changes, such as the impact corridor shifting continents or the probability crossing a trigger. Each update compares new values to the last values so trends are clear. If the risk drops, the update says why. If it rises, the update says what would reduce it. If it is steady, the update explains what is pending. The language is plain, no risk identified. Monitoring with low concern, increased attention due to improved orbit fit, and so on. The tone never chases headlines. It follows the data. Size and energy estimates get better with modest inputs. Photometry across multiple filters constrains color and, with reasonable assumptions about reflectivity, narrows size. A well-sampled light curve reveals rotation and shape clues. A large brightness variation suggests elongation, which affects how light scatters and thus the size estimate. Thermal infrared observations, when possible, split reflected sunlight from emitted heat and untangle size and albedo directly. Radar, if geometry and distance allow, can slash positional uncertainties and, in rare close cases, even image shape and spin, converting big ranges of outcomes into tight boxes. Each of these trims both the how big axis and the where and when axis, which directly feeds the scales. Not all risk is physical, some is about where people live. The same energy delivered over empty ocean is not the same societal problem as energy delivered near a city. So along with the physical scales, planners use exposure maps that overlay possible corridors with population density, critical infrastructure, and local terrain. This does not change the physics, and it does not belong on Torino or Palermo, but it helps prioritise follow-up resources when telescope time is limited. If two equally uncertain objects exist and one corridor passes near dense population, while the other crosses open ocean, the former gets earlier attention for refining the path simply to answer questions sooner. For airbursts, the atmosphere is the main actor. Models use entry speed, angle, strength, and size to estimate breakup height and overpressure at the ground. Overpressure is what breaks windows and can cause injuries from flying glass. Planners compare contours of overpressure to city layouts to sketch simple guidance like stay away from windows in a defined region if an airburst was still on the table late in the game. These contours come with confidence bands. As astrometry improves and the corridor tightens, the bands shrink. Most of the time, the updated corridor misses Earth entirely, and those maps go back in the drawer. When they are not needed, the same models become training material for the next drill. Interstellar visitors add one twist. Higher inbound speeds and less time in our neighbourhood. Higher speed raises theoretical energy, but the short passage and often steep angles reduce the chance of timing overlap with Earth. Practically, this means the initial Palermo values may look slightly less negative than for a slow-bound asteroid of the same size, but they still tend to be well below background because the time window is small. The response is the same: measure fast, refine the orbit, check for activity that could add non-gravitational forces, and retire the case as soon as the corridor misses. Because the window is short, observers coordinate across longitude, so probability estimates do not sit stale for a whole day, while the uncertainty could have shrunk. An important low-drama practice is value of information. Before chasing a hard observation, teams ask which decision it will change. If a challenging spectrum would not alter any readiness step, it can wait for science time later. If one additional astrometric point tonight will cut the impact probability by a factor of 10, or rule out Earth entirely, it gets priority. This keeps the process efficient and reduces the chance of wasting nights on data that won't move the scales. It also helps small observatories contribute in precise ways. A school telescope on the right longitude can be exactly what reduces the corridor at the right hour. Risk registers are living documents. Each object on a watch list has a brief story that records what was done, why it was done, and what happened. When the case is closed, the story remains as a lesson. Patterns emerge. Which cadences work best? Which filters give the most size leverage for faint targets? How often non-gravitational effects mattered? How to phrase public notes so they are clear to non-specialists? Over time, these stories turn into playbooks and then into checklists, the way aviation refined safety by learning from near misses and routine days alike. Finally, car measurement has a physical look and feel. It is a plot of probability versus time sloping down as new observations arrive. It is a corridor on a map narrowing until it slides off the Earth entirely. It is a table with the same fields week after week, mostly filled with zeros and small negatives, with the occasional bump clearly explained in a footnote. It is a shared understanding that scales are tools, not alarms, and that numbers are there to turn a scary-sounding phrase into a small, precise statement everyone can test and agree on. When people ask, "Is this dangerous?" the answer comes from that steady stack of plots, tables, and notes. Here is the current probability, here is the energy range if it were real, here is why we think it will not be, here is the next measurement we will make, and here is when we will tell you again. That is measuring danger calmly, and it is how the system stays both honest and reassuring at the same time. Earth's atmosphere is a thick, protective blanket that turns most incoming space rocks into light, sound, and dust before they ever reach the ground. As a small body dives in at hypersonic speed, it rams into air that becomes compressed in front of it. Compressed air heats up, the object's surface heats with it, and material begins to vaporize and peel away. This is ablation. At the same time, the rushing air pushes on the body with enormous force called dynamic pressure, written simply as Q. The faster the object and the denser the air, the higher Q becomes. When that pressure exceeds the object's strength, it breaks apart. These two processes, ablation and breakup, are the atmosphere's main defenses, turning solid mass into a spreading cloud that dumps energy high in the sky instead of on the ground. A useful mental picture is layers. Air is thinnest at the top and thickest near the surface. Early in the fall, the object is in very thin air. It heats, but the forces are still small. As it drops, air density rises quickly. The scale height of the atmosphere is only a few kilometers, so both heating and pressure climb fast. Heating roughly scales like air density times the cube of speed, so speed matters a lot. Pressure scales like air density times the square of speed. Because both terms grow with density, most of the energy is deposited in the stratosphere and upper troposphere, not at ground level. This is why you see bright fireballs high overhead and hear a sonic boom later. The light comes first from up high. The sound travels more slowly from the same region down to you. Size and makeup decide which branch the entry follows. Pebble to fist-sized meteoroids almost always burn up completely. They produce streaks and small shooting stars. Objects a meter or so across ablate and fragment into dust and tiny bits. They rarely reach the ground as anything larger than gravel. Tens of meters is the grey zone where strong material may produce an airburst with a shock wave that can break windows, while weaker, icy or porous material comes apart higher and spreads its energy over a wider area. Once you climb toward hundreds of meters, the atmosphere cannot remove enough mass or momentum in time. Fragments can reach the surface and create craters. These are broad conservative ranges that depend on speed, entry angle, composition, and internal strength, but they describe the overall pattern well. Entry angle is a quiet but powerful factor. A steep entry plows into dense air quickly, driving breakup lower and producing a stronger, more focused shock. A shallow entry skips through higher, thinner layers for longer, spreading the light and the pressure over a longer track and typically breaking up higher. Shallow paths can even glance out if very shallow and strong, but most real bodies fragment before that happens. This is also why two events with similar sizes can look very different from the ground. One booms loudly and rattles windows, the other is a long, bright sweep with softer sound reports arriving later. Material strength and structure decide on how fragmentation unfolds. A monolithic, coherent rock tolerates higher dynamic pressure and breaks later. A rubble pile or highly fractured rock shatters earlier. Icy or porous material heats and vents gas, which can hasten breakup. When the first major fracture occurs, the surface area of the swarm increases suddenly, and ablation accelerates. The swarm acts like a parachute, drag jumps, speed drops, and much of the remaining energy is transferred to the air as heat and shock, rather than to the ground. This catastrophic fragmentation is what produces classic airbursts, a bright flare, multiple peaks in the light curve, and a shock wave that arrives as booms and rumbles minutes later. The shock wave is the main cause of ground effects for most small to medium entries. Overpressure from the wave can rattle doors, set off car alarms and break glass. The level of overpressure falls quickly with distance and depends on burst altitude and energy. Communities have practical guidance tied to those numbers. Stay away from windows if a bright daylight fireball is observed. Do not crowd around glass to watch, expect a delay between the flash and the boom. These simple steps avoid most injuries in the rare cases where overpressure is strong enough to matter. Importantly, the same atmosphere that makes the boom also weakens it with distance. What starts as a violent shock at altitude becomes a set of softer waves by the time it reaches faraway towns. Light from the fireball is not just pretty, it is a measurement channel. The brightness over time, the light curve, reveals when major fragmentation happened. and how energy was deposited with altitude. Infrasound sensors, microphones tuned to very low frequencies, listen around the world and can detect airbursts, even over oceans or remote regions. Weather radars sometimes catch falling debris as it slows in the lower atmosphere. By combining optical, infrasound and radar data, scientists recover the energy of the event and estimate the original size and speed, all without needing a crater. This is atmospheric forensics, and it works because so much of the process happens in air rather than on the ground. Different surfaces below the path change details, but not the basic shield effect. Over land, the shock reflects from hills, buildings, and ground layers in complex ways. Over ocean, the surface is smoother, and energy couples into water less efficiently when the burst is high. A true water impact, fragments reaching the sea at high speed, can push up waves locally, but most small and medium bodies disintegrate aloft, never coupling strongly to the ocean itself. For large bodies, ocean depth, entry angle, and breakup height matter. Even then, the atmosphere has already bled off a large fraction of the energy before any remaining mass touches water. Speed is the lever that can make the same size object behave very differently. Typical asteroid entries are around 12 to 20 kilometers per second. Some comets and interstellar visitors can be much faster. Higher speed increases heating and pressure sharply. The good news is that higher speed also means earlier fragmentation for weak bodies, pushing the burst higher and spreading energy more. The bad news is that if a body is both fast and strong, the energy scale rises quickly. This is why composition clues, colour, spectra, and light curve behaviour matter for hazard models. They point to weak porous breaks high or strong cohesive breaks low, and those branches have very different ground footprints. You can think of the atmosphere as an automatic self-adjusting brake. If an object starts to push harder, the air pushes back harder. Drag grows with speed squared and density. As the object brakes, drag increases again. Every step tends to slow and spread. This feedback is why the real world delivers far fewer craters than space delivers rocks. Earth is hit constantly by dust and small stones. The atmosphere disposes of almost all of them quietly as meteors and small fireballs that never threaten anything on the ground. Simple rules of thumb help translate all this into everyday language. Tiny to meter scale burns and dusts out, nothing to worry about. Several meters to a few tens of meters, likely airburst, potential for window damage if low and energetic. Stay away from glass if you see a bright daytime bolide. Larger than that, case-by-case modelling with attention to strength and angle. Atmosphere still removes energy, but planning looks at corridors and, if needed, civil protection steps for a small region. These rules stay conservative on purpose and are refined when real measurements arrive. Finally, it is worth noting that this shield does not switch off at night or over the ocean, or in winter. It is constant and global. Weather changes details of observation. Clouds can hide a flash, winds can bend infrasound paths, but the physics of heating, drag and breakup do not depend on seasons or time zones. The sky is always doing this work for us. When we measure risk or explain events, we start by thanking that physics, ablation, turns mass into vapor, dynamic pressure turns boulders into confetti, shockwaves spend their power in high air, and most of what could have been a ground problem ends its story as a fading trail and a distant rumble in the sky. Impact physics boils down to a few simple levers: size, speed, density, and strength. Size sets how much mass there is. Speed matters even more because energy grows with the square of speed. Density tells you how heavy a given size is. Strength decides whether the object holds itself together or shatters high in the air. From these four ingredients, you can predict most of what matters, whether the event is a high-altitude light show, a loud air burst with a shockwave, or a rare ground impact that digs a crater. Kinetic energy is the headline number. It is 1/2 times mass times speed squared. Double the speed and the energy goes up by 4, double the size, diameter, and, for the same material, the mass goes up by 8, because volume grows with the cube of size. A rock 10 meters across, made of typical stone, coming in at 20 kilometers per second, carries on the order of 3 times 10 to the 14th power joules, roughly 70 to 80 kilotons of TNT, but the atmosphere will strip most of that energy high above you. A 50-meter rock at the same speed is around 10 megatons in raw energy. That is the right scale for strong airbursts. A 140-meter object lands in the few hundred megatons range if it were to couple its energy efficiently, which is why this size is used as a planning benchmark. Move to a genuine giant 1 kilometer across, and you are talking tens of thousands of megatons. Extremely rare, globally important events. These are ballpark figures to show the scaling, not predictions for any one case. Momentum, mass times speed, matters for how hard the object pushes on the air and ground. The air's response is captured by dynamic pressure, which grows with air density and speed squared. As the object dives, air thickens quickly. The pressure piles up on the front face. If that pressure beats the object's strength, it fragments. Fragmentation raises the total surface area, which speeds up ablation, material boiling and peeling away, which increases drag, which slows everything, which pushes more of the energy into the air instead of the ground. That cascade is why Earth's atmosphere is such an effective shield for anything below a few hundred meters. Entry angle tunes how and where the energy goes. A steep, fast entry plows into dense air sooner, breaks lower, and can produce a sharper shock at the surface. A shallow entry spreads the energy over a longer path and usually breaks higher, widening effects but softening the peak. Very shallow, very strong bodies can skip like a stone for a while, but real rocks tend to crack before they truly escape. Angle also changes brightness and the sound you hear. A long, grazing track gives a drawn-out fireball with rumbling minutes later. A steep, strong entry can give a short flash and a sharp boom. Strength and structure decide the branch of the story. A coherent, monolithic boulder resists pressure. It breaks later and more violently. A porous, icy or rubble pile body vents and crumbles early, turning into a debris cloud that acts like a parachute. The difference shows up in light curves, how brightness changes with time. A strong object often shows one big flare when it fails. A weak one shows multiple smaller peaks as pieces shed in stages. Colour and spectra help here too. Redder, spacer-weathered colours and the presence of gases like CN or OH point toward icy, comet-like behaviour. Weaker, earlier breakup. Stony inactive spectra often go with sturdier entries. Airbursts are mostly about shock waves. When a large fraction of the energy dumps in the stratosphere or upper troposphere, a blast wave races outward and downward. What matters at the ground is overpressure, how much the passing wave rises above normal air pressure. At around 1 kilopascal you hear and feel it strongly, and windows can rattle. At a few kilopascals, many windows break. Higher still and light structural damage begins near the track. Burst altitude is the big lever. Higher bursts spread wider and hit weaker. Lower bursts focus more and hit harder. Simple public rules follow from this. If a bright daytime fireball is seen, step away from windows and wait for the delayed boom. Most injuries in real events come from glass, not from fire or falling stones. If a body is big and strong enough to reach the ground at high speed, the physics shifts to crater formation. Cratering is a splash in rock. The initial transient crater is excavated by shock. Walls then slump and the rim settles into the final shape. On Earth, small craters, up to a few kilometers across, are simple bowls. Bigger ones collapse into complex craters with central peaks and terraced walls. The final diameter does not scale linearly with size or energy. It follows tested trends. Larger, faster and denser impactors make bigger craters. Softer target rocks make bigger craters than hard ones. Higher gravity, like on Earth compared with the Moon, holds craters smaller for the same impact. Most of the ejector lands near the rim, and the strongest damage footprint stays local, tens to a few hundred kilometers, unless the impactor is truly enormous. Thermal radiation from an entry is a small slice of the energy for most cases. The glowing plasma and hot fragments can be dazzling, but only a few % of the total energy goes out as light that could heat the ground. Burns or secondary fires are uncommon, except very near a ground impact or beneath a low, powerful burst. The big reliable effects are shock and wind. The bright light is mostly an observation channel that lets cameras and satellites measure timing and energy. Water entries deserve a separate note. For small and medium objects that disintegrate aloft, the ocean mostly sees an airburst, not a deep impact, so the main effect at the surface is pressure waves and spray directly under the track. A large, steep, deep water impact by a strong body can push significant water and make a hazardous local or regional wave, but that requires sizes where we already move from atmospheric shielding to civil protection planning, regardless of the surface type. Depth, angle, and breakup height are the key variables. Most realistic cases hand their energy to the air before they can efficiently couple into water. A few simple comparisons help anchor intuition. A compact car, about 1,500 kilograms, at highway speed 30 meters per second, carries approximately 700,000 joules. A 10-meter stone at 20 kilometers per second carries approximately 300 trillion joules. That is a factor of hundreds of billions more, which is why speed dominates the conversation. Now compare materials, swap a rocky body, about 3,000 kilograms per cubic meter, for an icy one, about 1,000, same size, 1/3 the mass, 1/3 the energy. That change alone can move a case from possible window breakage at low burst altitude to safe glow high in the sky. Uncertainties matter, but they shrink with modest data. A light curve with a clear spin period reduces shape guesses. 2 or 3 colours narrow reflectivity and thus size. A handful of precise positions over several nights tightens the entry angle and speed. With those in hand, models can bracket likely burst heights and overpressure contours without drama. If a target stays faint and the data are thin, planners keep assumptions conservative, stronger, denser, faster, and then relax them as soon as measurements say otherwise. Finally, it helps to picture the atmosphere as an automatic braking system that gets stronger exactly when you need it. Drag rises with speed, squared and air density. Fragmentation multiplies drag by making many pieces. Ablation scrubs off mass and carries energy away as light and heat aloft. All those feedbacks push outcomes upward and outward, rather than downward and concentrated. That is why tiny to meter scale rocks burn out. Why tens of meters rocks mostly airburst with limited ground effects. Why only larger, stronger bodies raise local ground concerns. And why the same basic physics keeps working day and night over land and sea, quietly turning most of the solar system's stray stones into brief streaks and soft rumbles instead of disasters. The core of planetary defense is simple. Find hazardous objects early, learn their properties quickly, predict their paths precisely, and have realistic options both in space and on the ground when action is needed. Everything else in the toolkit serves one of those 4 goals. Early discovery comes from wide-field surveys that scan the sky on repeat cycles, building nightly catalogues of moving points of light. These optical surveys work best when many telescopes with different apertures share the load. Small, fast systems cover huge areas to catch new movers. Medium telescopes confirm and extend the arc that pins down orbits. Large telescopes probe faint details like colour and activity. Soon, thermal infrared surveys from space add what the ground cannot, a direct read on heat, which helps separate size from reflectivity. Together, these instruments convert a dim streak into a well-measured object with an identity, a preliminary orbit, and a to-do list for follow-up. Characterization is the next layer. Photometry across multiple filters yields colour indices that hint at surface materials. Time series photometry builds light curves that reveal rotation periods, shape elongation, and tumbling states. Spectroscopy, when brightness allows, identifies gas species in active objects and the reflectance slopes of inactive ones, tying them to known asteroid or comet classes. Radar, If the geometry and distance cooperate as a force multiplier, range and Doppler measurements can shrink orbital uncertainties by orders of magnitude in a single session, and echo shapes can reveal size, spin index, and even surface roughness. In thermal infrared, the balance between emitted heat and reflected sunlight constrains diameter and albedo directly. Each of these measurements turns a hypothetical worst case into a bounded, evidence-based scenario with fewer surprises. Orbit determination and continuous monitoring keep the picture honest. Precise astrometry anchored to modern star catalogues feeds orbit fitters that return both a nominal solution and a covariance matrix, the uncertainty map. Automated systems propagate the orbit forward, search for close approaches, and post results on public risk pages so any expert can reconstruct the calculation. When an object stays interesting, the network schedules more astrometry at the most informative times and longitudes, leaning on the line of variation, where one added measurement collapses the uncertainty fastest. If non-gravitational forces like outgassing or radiation pressure appear in the residuals, analysts add gentle acceleration terms to the model and test whether the fit genuinely improves. The result is a living trajectory that hardens with time, reducing both false alarms and false comfort. Mitigation in space divides into slow push, quick push, and last resort. Slow push methods operate gently over months to years. A gravity tractor is a spacecraft that hovers near the object and uses mutual gravity as a tug, firing its thrusters to maintain station while transferring a tiny but steady momentum to the body. Because the force is small, this method needs long lead times and works best for modest-sized targets discovered early. Variants include ion beam shepherding, where a spacecraft's thrusters are aimed at the surface so the exhaust acts like a wind, and surface attachments that pull or push directly if the regolith will hold anchors. Another slow concept is changing reflectivity, painting patches or laying reflective film so sunlight's tiny but relentless push, the Yarkovsky effect, alters the orbit over years. These techniques share three virtues: fine control, low risk of fragmentation, and reversibility if the sign or magnitude of the effect needs adjusting. Quick push methods act in a single event. Kinetic impactor strikes the object at high relative speed to transfer momentum. The effectiveness depends on the mass and speed of the impactor, and on how much ejector the impact throws out in the sunward or anti-sunward direction. Ejector can multiply the deflection by acting like a rocket plume. This approach demands accurate navigation, a known impact geometry, and enough warning to launch and cruise to the intercept point. It benefits from prior reconnaissance. A small scout craft, or even a rideshare CubeSat, can arrive first to map shape, spin state and surface texture, turning a risky blind hit into a precise maneuver. Quick push fits the middle ground, not enough time for a tractor, but still months to years before the predicted encounter. Last resort means nuclear devices used in space, typically in a standoff configuration where the device detonates near, not on, the object. The intense radiation ablates the surface facing the burst, creating a high-velocity sheet of vapor and ejector that imparts a strong momentum change without physically fragmenting the body. This option offers the largest deflection per unit mass and the shortest timelines, which is why it appears in serious studies alongside its legal, political, and operational complexities. Fragmentation risk is managed by choosing standoff distances and angles that maximize momentum transfer while minimizing sprawl. Because this tool sits inside strict international treaties and requires extraordinary cooperative decision-making, planning documents treat it as a case to be deeply rehearsed on paper, carefully simulated, and never normalized, while acknowledging that it may be the only effective lever for very late, very large threats. Any space method depends on time. Lead time is the currency of mitigation. Years are ideal, slow push becomes feasible, launch windows are plentiful, redundancy is affordable, and multiple opportunities to measure, adjust, and remeasure exist. Months can still work for kinetic impactors if hardware is on the shelf and trajectories align, but margins shrink. Weeks moved the emphasis from deflection to civil protection because a safe, reliable space mission cannot be conjured from scratch on that timescale. The toolkit therefore includes readiness measures that are not rockets, pre-approved mission designs and buses that can be adapted quickly, trusted navigation software, trained operations teams, and international agreements that define who asks whom for what when certain thresholds are crossed. Civil protection is a first-class tool, not a backup. If models show only an airburst potential, the safest move might be targeted guidance, simple messages like avoid windows and expect a delayed boom delivered to regions under a narrow corridor timed to when the sound will arrive. If a small but non-zero chance of a ground impact lingers close to decision time, authorities can move people and critical operations out of a corridor days in advance, the way coastal towns respond to hurricane forecast cones. For larger cases where local damage is possible, the same playbooks used for industrial explosions and severe weather apply: sheltering guidance, transportation reroutes, and temporary closures. Good civil protection depends on clarity and cadence. Updates at known times with map products that show what changed, what did not, and what to do next if probability thresholds move. International coordination holds the system together. Discovery networks post alerts in machine-readable formats. Follow-up observers in other countries pick up the baton as night falls westward. Modelling centres turn measurements into probabilities and share them. Space agencies assess mission options. Civil authorities prepare guidance. And public information teams keep language consistent. Standing groups agree on vocabularies, thresholds, and responsibilities before any real case appears. Regular exercises, tabletop and live, run mock scenarios end to end. A faint discovery becomes a candidate. Probability rises. Wording is drafted. Telescope time is reallocated. A mission concept is sketched. Then new data remove the risk and the system stands down. Each exercise ends with the notes that fix real bottlenecks, like out-of-date contact trees, missing translation templates, or data formats that slowed handoffs. Modelling and simulation are essential instruments in their own right. High-fidelity entry models turn size, speed, angle, and strength into burst heights and ground-over-pressure contours with uncertainty bands. Impact scaling laws translate energy and geology into crater size and ejector patterns. Deflection mission simulators propagate spacecraft and target together under realistic navigation errors, thrust misalignments, and uncertain surface response, returning not just will it work, but how robust is it if we guessed part of the physics wrong. Monte Carlo frameworks wrap these pieces to explore thousands of variants, so planners see not a single optimistic path but a thick bundle of overlapping feasible plans. Data infrastructure keeps tools sharp between crises. Survey pipelines are tuned so false positives stay low while sensitivity stays high. Astrometric standards evolve as catalogues improve. Open databases store light curves, spectra, radar shapes, and thermal measurements with uniform metadata, so old targets can be reanalyzed when new techniques arrive. Versioned ephemerides and uncertainty products make it trivial to reproduce past results. Amateur and university observatories are integrated with clear contribution guides. When a small instrument at the right longitude can meaningfully reduce an orbit corridor, instructions and exposure settings are ready, and credit flows back to contributors to keep the community motivated and skilled. Hardware readiness is its own shelf in the toolkit. Launch vehicles with known performance envelopes, spacecraft buses with flight heritage, autonomous optical navigation packages, high-thrust and high-efficiency propulsion options, and deep space communications that can handle short-notice operations all reduce calendar risk. For kinetic missions, kinetic kits, impacting spacecraft designed to be rapidly configured for different targets, cut design time. For slow-push, standardized tractor buses with modular thrusters and power systems make long-duration station keeping more routine. Even a small reconnaissance craft designed to piggyback on either path is a force multiplier, turning unknowns about surface strength, regolith behaviour and spin state into measured inputs before the main act, policy and law round off the set, clear criteria for when to escalate, how to share sensitive but time-critical data, how to assign leadership and liability for mission actions, and how to coordinate cross-border civil measures, keep focus on physics rather than process during a real case. Templates for public messages in multiple languages, pre-negotiated spectrum allocations for radar campaigns, and arrangements for airspace and maritime safety notices during low-probability corridors are boring in the best way and invaluable when hours count. After-action transparency, publishing what was known, when, by whom, and what was done, builds trust and improves the next response. Education and outreach keep the human side resilient. When people understand that discovery is constant, that most objects are harmless flybys, that scales like Torino and Palermo exist to de-dramatize numbers, and that practical guidance for rare airbursts is as simple as step away from windows, rumour loses its grip. Teachers, museums, and media partners who can explain entry physics with kitchen table examples turn a frightening headline into a science lesson. That too as a tool, it lowers the social cost of false alarms, speeds some's acceptance of stand-down decisions, and makes it easier to act decisively on the rare day action is warranted. In the end, the Planetary Defense Toolkit is not one silver bullet, but a layered system. Find early with wide surveys on Earth and in space. Characterize quickly with colours, spectra, thermal data, and radar. Track precisely with disciplined astrometry and shared models. Plan flexibly with slow and quick space options sized to the timeline. Protect people on the ground with clear, practiced civil measures. Coordinate internationally with exercised roles and transparent updates. And keep the whole machine ready through steady investment in data, hardware, law, and public understanding. Each layer reduces risk on its own. Together they turn a nightmare-sounding question into a set of manageable engineering and communication tasks carried out with the same calm procedures every time. Interstellar visitors differ in four main ways: how they move, how long we can see them, what they are made of, and what kinds of risks or opportunities those differences create. The first and the most obvious difference is speed. Because they are not bound to the Sun, they arrive with a non-zero excess velocity, even far from the solar system, tens of kilometers per second before the Sun's gravity adds or subtracts a little. That higher baseline speed makes them sweep across the sky quickly, so our observing window is short and our ephemerides need frequent updates. The same speed also means their orbits are open hyperbolas instead of closed ellipses. So there is no repeating loop, no next apparition, and no resonant return keyholes that could set up a future hit years later. From a risk standpoint, that last point is actually helpful. There is no long-term chaining of encounters. Either the timing lines up during this single pass or it does not, and most of the time it does not. The second difference is geometry. Many small bodies native to the solar system live near the ecliptic plane where the planets orbit. Interstellar objects can approach from any angle, high inclination or even retrograde relative to the planets. High inclination paths cross Earth's orbit quickly at a steep angle, which shortens the time in our neighbourhood and reduces the chance of being in the same place at the same time as Earth. That steep geometry also changes the phase angles at which we view the object, Sun-object-Earth angle, reshaping how bright it looks and how its light curve behaves. Observers compensate with non-sidereal tracking, rapid cadence, and track and stack, but it does make everything feel time-compressed. Third is composition and surface history. A body that formed around another star spent eons in different radiation, temperature, and collision environments. That could mean unfamiliar blends of ices, organics, and minerals, different porosity, and surface skins that have been baked or sputtered in ways we do not often see here. Practically, this adds uncertainty at first. Will it behave like a fragile icy comet, early breakup, fuzzy coma, or like a compact inert rock, clean point source, later breakup? Photometry across filters, spectra if brightness allows, and careful light curves narrow that down. In many cases, the physical behaviour lands in familiar categories, weak and dusty or sturdy and dark. But the outliers are scientifically valuable because they test the limits of our models about how small bodies form and age. Fourth is the trade between speed and focusing. Fast approach speeds do raise the raw kinetic energy scale, but they also reduce gravitational focusing by planets. Gravitational focusing is the way a planet's gravity enlarges its effective target size for slow movers. The slower the object, the more time gravity has to bend it inward. Quick interstellar arrivals experience less of that pull on their way by, which trims the reach of close approach corridors. Combine that with steep, brief crossings of Earth's orbital plane, and you get a practical outcome that surprises people. Despite the higher speed, the odds of impact during the single pass are typically lower than for slow-bound asteroids that keep coming back for repeated chances. From a safety angle, different does not automatically mean worse. Where interstellar is harder is logistics. The short window means we must pivot fast, confirm the orbit, rather than to refine it nightly and squeeze in characterization before the object fades or moves into dawn. Exposure times are limited by motion blur. Ephemerides go stale in hours for faint targets. The best spectra may require large telescopes that need rapid scheduling. Coordination across longitudes becomes essential so that the world's night follows the object, handing off observations as Earth turns. This urgency does not increase physical danger. It increases the challenge of gathering enough data to answer questions quickly and communicate clearly. Atmospheric entry physics also shifts in predictable ways. Higher speed increases dynamic pressure and heating, so weak bodies fragment higher and more completely, favouring airbursts that deposit energy aloft. Strong bodies carry more energy, but they also spend less clock time in thick air because of the steep, fast geometry, which spreads the pressure footprint along a shorter path. The atmosphere's automatic brake, drag rising with speed squared and density, ablation scrubbing mass, fragmentation multiplying drag, still dominates for small to medium sizes. The branching remains the same as for native objects. Tiny to meter scale burns out. Tens of meters airburst with shock waves that diminish with distance. Only larger, stronger bodies raise local ground concerns. In other words, the rules do not change, the coefficients do. On the modelling side, the lack of future returns simplifies some tasks and complicates others. Simplified, there is no need to map multi-year resonant keyholes or chain a decade of encounters. Once the passing window closes, the case is over. Complicated, the orbit must be nailed down quickly from a short arc, sometimes with non-gravitational nudges from outgassing that are hard to measure when data are sparse. Teams hedge by running Monte Carlo clones of the orbit early and often, posting corridors and confidence bands that shrink as follow-up arrives. Because the timeline is compressed, the value of information calculation becomes sharper. One well-placed night of astrometry can retire entire branches of concern. Detection bias plays a role too. Our surveys are tuned to find things that linger and brighten on repeat nights. Interstellar objects do not linger, so we rely on wide fields, fast cadence, and low false positive rates in the subtraction pipelines. When the pipeline prioritizes moving but faint and fast, the candidate list expands, but so do artifacts. Machine learning filters, human broker checks, and rapid cross-observatory confirmation keep efficiency high without crying wolf. The survey sensitivity increases, especially with next-generation wide fields and space-based infrared. Discovery rates will rise, and so will the fraction caught earlier and farther out, which stretches the window and makes everything easier. From a mitigation perspective, interstellar is mostly a communications problem, not a hardware problem. The high-speed, single-pass nature means there is almost never a realistic deflection timeline unless the discovery happens very early and the object is modest in size. Fortunately, the same dynamics that make deflection unlikely also make impact unlikely, so the operational focus is on swift, clear updates. What we know, what we do not, where the corridor is today, and what observation will shrink it next. If a corridor persists late and implies only an airburst, civil protection guidance looks exactly like it does for native airbursts. Stay away from windows beneath the track, expect a delay before the boom, and carry on. If a larger case ever remained, the same playbooks apply, just on a compressed schedule, with more emphasis on rapid ground measures than on space missions. Scientifically different is a big win. Each interstellar visitor is a free sample from another planetary system's workshop. Colours, activity, spin states and surface strength feed models of how planets form, how small bodies are ejected, how materials weather in interstellar space, and how common certain chemistries are. Even null results, no detectable activity, colours within native asteroid ranges, light curve consistent with a compact shape, are powerful because they constrain the variety out there. Over time, a small catalogue of well-measured interstellar objects will let us test whether other systems tend to shed more comet-like debris, more rock-like debris, or a mix, and how that mix changes with the age or type of the parent star system. Finally, it helps to put different into a plain balanced sentence. Interstellar objects arrive faster, at odd angles, and give us less time to watch. That makes the observing and communication work feel urgent. They do not loop back, they experience less gravitational focusing, and they cross our orbital plane quickly. That usually lowers practical impact odds compared with many homegrown asteroids. The atmosphere does its normal job the same way regardless of passport. The main change for us is pace, not peril. With wide surveys, quick follow-up and steady public notes, Interstellar becomes what it mostly is, a rare chance to learn about other solar system, wrapped in a brief logistics sprint that ends with a clean flyby and a thicker, calmer playbook for next time. When a small icy body warms, the quietest chemistry turns visible. Ices near the surface sublimate, gas seeps through pores, and sunlight and vacuum lift dust from weak spots to build a hazy envelope called the coma. In images, a coma looks like a soft, round glow centered on the nucleus, fading outward. Its brightness typically drops roughly like 1/ρ. Rho is distance from the center in the image, because fresh molecules are produced near the nucleus and then spread out. Mixed into that glow are fine grains, micrometer to millimeter scale, released by gas drag or by brittle crusts cracking as day-night temperatures cycle. The coma feeds one or more tails, and those tails are signposts of the physics at work. Dust listens to sunlight, gas listens to the sun's magnetic breath carried by the solar wind. Together they record composition, activity level, and even the spin and seasons of the source. Dust tails are sunlight stories. Each grain feels gravity pulling inward and radiation pressure pushing outward. The ratio of those forces is called beta. Tiny grains have large beta, so they get shoved away quickly and bend into broad fans that curve gently. Bigger grains have small beta, lagging closer to the orbit like a slow snowfall. Because every release moment and grain size makes a slightly different track, a dust tail is a layered history. Analysts draw syndines, constant beta, and synchrones, constant release time, to decode when and how grains left the nucleus. A related quantity, AFRO, combines dust albedo A, the filling factor of grains in the aperture F, and the projected radius ρ to give a simple distance-independent proxy for dust production. Higher AFRO means a dustier coma. At small Sun object Earth angles, dust looks compact. At larger phase angles, forward scattering makes the coma and tail brighten and the colours redden, revealing grain-sized distributions and porosity. Polarimetry adds another layer. By measuring how scattered light is polarised as a function of phase angle, we infer whether grains are fluffy aggregates or compact particles. Gas tails are electricity stories. Neutral molecules stream out, but sunlight quickly breaks and ionises many of them. Once charged, they feel the interplanetary magnetic field frozen into the solar wind and are swept into long, straight plasma tails that point roughly anti-sunward with sharp structure. These tails can disconnect abruptly when solar wind conditions change, snapping and reforming as a coronal mass ejection or a sector boundary sweeps past. The glowing bands we record in spectra, like CN near 388 nanometers, the swan bands of C2 around 516 nanometers, NH and NH2 features, sodium D lines near 589 nanometers, and the OH band near 308 nanometers are fingerprints of parent ices H2O, CO2, CO, NH3 that photodissociate into daughters OH, CN, etc. Because some key bands sit in the ultraviolet, space telescopes and specialized ground filters are used when possible. With a simple Hazer model, observers turn line fluxes into production rates. For example, Q of H2O, Q of CO2, Q of CO, compare them night by night and watch which volatile is driving activity at a given heliocentric distance. CO and CO2 can lift dust far from the sun where H2O is still frozen. H2O takes over inside approximately 3 astronomical units as temperatures rise. Morphology in the coma, fans, jets and spirals maps the nucleus's landscape and spin. Active regions at specific latitudes vent more strongly when illuminated, so as the nucleus rotates, a jet traces a corkscrew pattern projected onto the sky. By measuring the spacing of spiral arcs and knowing the outflow speed of gas or dust, we estimate rotation periods and sometimes precession or tumbling. Seasons matter too, as the subsolar latitude migrates over an orbit. One hemisphere can wake while the other sleeps, turning jets on and off and shifting the dust colour as different terrains contribute different grain sizes. In some objects, a refractory mantle of dust forms over time, stifling gas escape until cracks or impacts open vents again. This on-off hysteresis is common and explains why activity can persist after perihelion as stored heat leaks from the subsurface. Colour is chemistry's shorthand. Broadband colours, e.g. G-R, R-I, track dust reddening, which tends to rise with grain porosity and size. Narrowband filters isolate gas emissions from the dust continuum, letting small telescopes map CN or C to jets even when the nucleus itself is unresolved. Thermal infrared data, when available, separate reflected sunlight from emitted heat. The warm dust continuum peaks in the mid-IR, constraining grain sizes and temperatures and breaking the diameter albedo degeneracy for an otherwise point-like nucleus. Radar rarely sees comets unless they pass quite close, but when geometry cooperates, it weighs large grains in the innermost coma and, in exceptional cases, silhouettes the nucleus, anchoring size and spin. Dust dynamics do not end at the tail's edge. Over months, large grains shed near perihelion settle into a narrow trail that follows the orbit rather than pointing away from the sun, distinct from the broad tail. Trails are reservoirs for future meteor streams. If the Earth crosses that path, we meet those grains as meteors with shared speeds and radiant points. The grain lifetimes are modulated by pointing Robertson drag and collisions, slowly tightening the stream and shifting it sunward over many revolutions for bound comets. For a one-time interstellar visitor, there is no long-term stream near us, but released dust still obeys beta and paints a brief, modelable fan that tells us when activity started and how vigorously it ran during the weeks we could watch. Not every active-looking object is a classic comet, and not every interstellar visitor will sprout a textbook tail. Some small bodies are active asteroids where dust is lofted by fast rotation, impacts, or ice in trapped pockets. Their comae are dust-dominated, with little or no gas in spectra. Others carry ices but remain mantled or simply too cold at discovery to outgas strongly. In such cases, careful point spread function analysis compares the object's width to nearby stars. Even a subtle coma broadens the profile. If a faint, narrow anti-tail appears, apparently pointing sunward, that is not gas flowing uphill. It is a projection effect seen when Earth crosses the object's orbital plane and we look edge-on through the dust sheet, a geometry lesson that rewards patient imaging over several nights. Quantities that look abstract on paper translate directly to pictures. Increase beta, the dust tail curves more and extends farther, the coma reddens. Increase gas production, the plasma tail sharpens, and narrowband images brighten in CN or OH. Raise the phase angle, forward scattering lights up the dust like fog in headlights. Shift heliocentric distance outward. H2O bands fade. CO/C. O2 features persist longer if those ices are present, and dust grains get larger on average because weak gas flows can't lift the smallest particles. Add solar wind drama. The ion tail kinks or disconnects and then regrows. Each of these changes can be recorded by the modest telescopes with the right filters and cadence, which is why amateur professional campaigns matter. They turn nightly snapshots into time-lapse physics. From tales to truths, the path is modelling. Finson-Probstein dust codes launch grains of various beta at measured times, letting radiation pressure and gravity sculpt synthetic tails until one matches the shape and brightness profile we see. Gas models couple photochemistry, parent to daughter lifetimes under sunlight, with simple outflow to predict how CN or OH should fade with distance from the nucleus. When data meet model, we extract grain size distributions, dust to gas ratios, total mass loss and active area fractions on the nucleus. Those numbers then feed thermal models of the surface, how thick a dust mantle must be to stifle H2O at certain distances, how deep heat penetrates between day and night, and what patch sizes best reproduce the observed jet patterns. For an interstellar object, these same tools become passports. A coma rich in CO at large distances hints at formation in a cold far zone of another system. Unusually low CO with early H2O suggests different layering or long interstellar processing that drove off the most volatile ices. A high dust-to-gas ratio with very red porous grains implies gentle surface processing and fragile aggregates. A compact, neutral-coloured coma implies sturdier, perhaps rockier material. If spectra remain blank and only continuum appears, we still learn from light curves, colours and tail geometry. A dust-only fan tells us gas was present but too sparse to glow. A bare point with no broadening tells us activity stayed below detection, letting us limit the size of any exposed ice patches. Finally, all of these measurements nest inside a practical observing plan. Start wide with broadband images to detect any coma and measure AFRHO. Add narrowband or low-resolution spectra to pick out gas bands if present. Schedule repeated visits to build light curves and watch for jets rotating. Vary apertures to track the 1/ρ coma profile. And coordinate across longitude so phase angle and geometry changes can be separated from true activity shifts. If the object is faint, track and stack on its motion to avoid smearing, and compare the stacked profile to stars for subtle coma detection. If brightness allows, extend to thermal IR for dust temperatures and to polarimetry for grain structure. The result is a layered, cross-checked picture, where dust tells the story of sunlight and grain physics, gas tells the story of ices and chemistry, and the tail as a whole becomes a moving diagram, a live, gentle experiment in how star heat and vacuum rewrites small bodies in real time, turning hidden composition into visible, measurable light. Simulations turn faint dots and noisy measurements into testable futures by encoding physics in equations, and then letting those equations run forward many different ways. The simplest layer starts with orbits. An orbit model takes positions on the sky and times, solves for the 6 elements that describe the path, and carries along the uncertainty in those elements. To explore what might happen next, the model samples thousands of slightly different starting states, an ensemble consistent with the measurements, and integrates each one forward under gravity. This is an n-body problem when you include the Sun, planets, and sometimes large asteroids. It is solved with numerical integrators designed to be both accurate and stable over the short windows that matter for a passing visitor. The outcome is not a single line but a bundle of lines, a corridor that shows where the object could be night by night and how that corridor tightens as fresh data arrive. Good simulations never hide their uncertainty. Each ensemble member is a hypothesis. If the true orbit is this, then tomorrow the object is here. By comparing the simulated footprint on the sky to new observations, the model promotes the hypotheses that agree and demotes or discards those that do not. This is data assimilation in practice. In simple form, it looks like recalculating the orbit after every new night. In more formal terms, it can be a Kalman filter, an ensemble Kalman filter, or a particle filter that updates the probability distribution over states. The key idea is the same. The simulation believes the physics, but lets the data pull it back on track so predictions do not drift away from reality. Gravity is the backbone, but not the whole story. Some objects outgas, adding a tiny push that a pure gravity model cannot see. Simulations test both cases, with and without a non-gravitational acceleration term aligned roughly away from the Sun. If residuals, the small differences between predicted and measured positions, drop when that term is included, it stays. If not, it goes. Radiation pressure on very low mass fragments is treated similarly. These are modest corrections, but over weeks they can shift a predicted close approach by thousands of kilometers, so the simulation carries them as optional, evidence-driven knobs rather than fixed assumptions. On the ground-facing side, trajectory ensembles feed entry and airburst models. Here the physics switches from celestial mechanics to high-speed flow, heating and material failure. A common approach is to treat the entering body as a point mass with drag, lift usually small, ablation, and a strength that sets when it fragments. The model ramps air density with altitude, increases dynamic pressure with speed, and marks breakup when pressure exceeds strength. After breakup, the mass becomes a cloud of fragments with far more surface area. Drag jumps, speed falls, and energy is deposited higher. Running this for many entries, fast versus slow, shallow versus steep, strong versus weak, produces distributions of burst heights and overpressure at the ground. Those distributions become practical maps with confidence bands rather than scary certainties. For special studies, hydrocodes and computational fluid dynamics go deeper, resolving shock structures, fragment interactions, and the chemistry of ablation products. But the fast, semi-empirical models are the workhorses because they can sweep thousands of possibilities in minutes. For the rare large cases where cratering matters, scaling laws link impact energy, impact angle, target rock properties, and gravity to transient and final crater sizes. These laws are distilled from laboratory shots, nuclear test-era cratering data, and high-fidelity simulations. A simulation does not claim a single diameter. It returns a range with clear dependence on inputs, so planners can see how sensitive outcomes are to, say, a change from porous to competent rock, or from a 35-degree entry to a 60-degree entry. Sensitivity analysis, Sobel indices, one-at-a-time sweeps, and Latin hypercube sampling ranks which inputs actually move the outputs, guiding observers toward the measurements that matter most for shrinking error bars. Because time is always short with interstellar visitors, simulators lean on speed-ups. Symplectic integrators preserve orbital structure while taking bigger time steps for the gravity part. GPU-accelerated pipelines fling thousands of orbit clones forward in parallel. Reduced-order models and surrogate emulators, Gaussian process or neural network stand-ins trained on a library of expensive runs, predict burst heights or overpressure contours in milliseconds for new input combinations. This is not guesswork. The surrogate sits on top of validated physics and advertises its own error, so analysts know when to fall back to the full solver. The result is a loop that can keep pace with nightly updates, new astrometry in, ensemble refreshed, corridor revised, entry statistics updated, map tiles regenerated, and the next value of information calculation produced by morning. Value of information is not a slogan. It is a query the simulation answers directly. If the corridor on the sky is long and skinny, where along that line would one more measurement collapse the future most? If the size range is wide because albedo is unknown, how much would a thermal infrared observation narrow the diameter? And how would that propagate into burst altitude and over pressure uncertainty? If non-gravitational terms were ambiguous, what cadence and filter set would distinguish outgassing from noise? By quantifying how much each hypothetical observation would shrink the spread of outcomes, the model turns telescope time into a ranked shopping list rather than a guess. Simulations also handle the "what if we intervened" branch. For kinetic impactors, the code adds a small impulsive velocity change at the intercept time and direction, then propagates the altered orbit and its covariance to the encounter date. It samples impact geometry uncertainties, ejector momentum multiplication factors, and navigation error to produce a cloud of post-deflection futures rather than a single red line. For gravity tractors or other slow-push methods, the model applies a low, continuous force over months, integrates the coupled spacecraft-asteroid motion, and shows how early and steady beats late and frantic. If timelines are too short for space missions, the simulation shifts to civil protection products. Entry corridors, burst height distributions, and ground over pressure bands aligned with population and infrastructure layers so local authorities can see concretely what "stay away from windows" or "clear this narrow corridor" would mean in space and time. Underlying all of this is calibration. A trustworthy simulator is anchored to past events with known energies and geometries, so that its parameters are not free to wander. Bright bolides recorded by multiple sensors, well-observed comet outbursts, radar-measured near-Earth asteroid flybys, and deliberate tests in space provide anchor points. The code is run against these cases with inputs blinded where possible, and residuals are published so that users know the typical bias and scatter. When the model misses, the miss becomes a patch note and a new constraint. Update the ablation law, adjust the fragmentation prescription, refine the thermal inertia assumptions, or correct a star catalogue bias that crept into astrometry. This culture of test and tell keeps simulations honest and improves their bite-sized guidance for the next live case. Because ensembles can be large, results are summarized with products tuned to decisions rather than to raw physics plots. A sky map with an uncertainty ribbon and time ticks, a table showing percentile burst altitudes and associated overpressure footprints for representative sizes and strengths, a small set of ephemerides with validity windows and tracking rates so observers waste no time, a one-page delta that lists only what changed since yesterday, corridor shift, probability swing, size range update, any detected activity, and the single most useful next observation. For mission branches, a dashboard of lead time versus achievable deflection for different methods, with green, yellow, and red regions that reflect hardware readiness rather than theoretical possibility. The goal is to make the river of numbers feel like a steady rhythm. Predict, observe, update, repeat. So no one confuses motion with progress or drama with risk. Even the prettiest simulation is just a mirror for our assumptions, so the teams who run them keep a short list of humility checks. Are we exploring the tails of the distribution, not just the median? Did we allow for model form error, not only input error? Are we double counting confidence by reusing the same data to both tune and test? Are we publishing the code version and input catalog so others can reproduce our exact maps? Are we clear about what the model cannot see? Small jets that change spin states, fragmented shapes that invalidate a point mass entry approximation, or rare material behaviors outside our calibration range? Writing these limits down in the same place as the plots is not a weakness. It is part of why the plots deserve trust. Finally, simulations are most useful when they are quiet, iterative companions rather than one-off spectacles. They keep cadence with the sky, a nightly chore that folds in new measurements, trims away implausible futures, and returns a smaller, clearer set of possibilities. They give observers a precise place to aim and a good reason to aim there. They give communicators numbers that stay put long enough to explain without confusion, and they give planners branching paths with timings and margins attached, so that if this, then that becomes a short, reliable list rather than a fog. In that sense, dreaming with equations is not about predicting the extraordinary. It is about making the ordinary work so smoothly that when something truly unusual happens, the numbers, the people, and the plans are already moving in step. News about space rocks follows a familiar pattern. A small technical update becomes a big emotional headline, and somewhere in the middle the meaning gets bent. This is not because anyone is foolish. It is because our brains like vivid stories and simple labels, while orbital mechanics and probabilities are neither vivid nor simple. A measured voice starts by translating the core ideas into stable, repeatable language. What was seen, how often it was seen, how sure we are, how big it might be, when it would matter if it mattered at all, and what will change the picture next. The aim is to lower the temperature without lowering the truth. When we do that, myths lose their grip, and the story becomes clear enough that people can follow along without anxiety. One useful distinction is between possibility and probability. Possibility pulls headlines because it is binary, could or couldn't. Probability is boring because it is a fraction that can shrink quietly. Early after discovery, many possibilities remain. That is normal. The right sentence is, right now, many paths are mathematically consistent with the few measurements we have. As we add nights, most paths will disappear. If you instead say object could hit Earth, you did not lie, but you left out the part that matters most, the fraction and the trend. Measured voices attach numbers and directions like 1 in a million and falling as more data arrive, and they repeat those numbers on a schedule so people see this decline. Another anchor is the difference between close in sky maps and close in daily life. A plot can show a line skimming Earth's orbit and look alarming, but that is a lane map, not a rendezvous. You need both the same lane and the same time. A measured update says, the object's path crosses Earth's orbit, but it will be on the far side of the Sun when we are here. Or, the minimum orbit intersection distance is small, but the timing does not overlap. Simple drawings help. 2 trains, 2 tracks, 1 timetable. Myths thrive on the picture of crossing lines. They fade when a clock is drawn on top. Scales exist because adjectives fail. Words like tiny, unlikely, and safe mean different things to different people. The Torino and Palermo scales force consistency. A measured voice uses them exactly as intended. Torino 0 or 1 with a plain language gloss, normal discovery, no special concern. Palermo negative with a reference to background rates. If a value changes, the update explains whether the change came from better size estimates, a longer time arc, or the inclusion of a small non-gravitational push in the fit. Myths prefer mysterious jumps. Measured voices walk through the reason and show the before-after plot. A common myth is that governments hide dangerous objects. In practice, asteroid astrometry orbits and risk pages are public and mirrored around the world. The healthiest habit is to point to those public dashboards and show how to read them, where the probability appears, what the confidence interval means, why entries vanish when a case is retired. If a case lingers, the message is not secrecy. It is stubborn uncertainty that needs more photons. A measured voice tells people exactly which observation, another night of positions, a thermal pace, a radar ping, if geometry allows, would shrink that uncertainty fastest, turning trust me into help the network by understanding what we're waiting for. Another myth is that interstellar equals especially dangerous. It sounds dramatic because it is rare. The measured counterpoint is mechanical. Higher speeds, less gravitational focusing, brief plane crossings, and no resonant returns make impact odds per object lower, not higher than for many bound near-Earth objects. The urgency applies to data collection, not to danger. We have less time to learn, not more reason to panic. Keeping the logic on the table, speed raises energy but lowers focusing, single pass means no chained encounters, keeps the discussion from drifting into sci-fi. Media incentives reward novelty, and astronomers stunned is a reliable phrase even when the real mood is astronomers interested. You can't rewrite incentives, but you can flood the zone with specifics. Put numbers next to verbs. Observed on 7 nights. Arc length now 5.1 days. Size range narrowed from 50 to 150 meters to 40 to 70 meters. Impact probability from 1 times 10 to the minus 5 to less than 1 times 10 to the minus 7. Torino from 1 to 0. Make the plot that shows the uncertainty corridor shrinking night by night and post it at the same URL in the same format until the case closes. When that plot is dull, you're communicating well. Social media compresses nuance into screenshots. This is where myth correction needs pre-built tiles. 1 square for what MOID is and is not. 1 for why early probabilities can wobble. 1 for airburst versus ground impact. 1 for what to do if a daylight fireball appears. Step away from windows, wait for the boom. 1 for how to read Torino/Palermo. And 1 for what changes the forecast. These tiles work because they let you respond without drafting under pressure. You're not inventing clarifications on the spot. They also create a look and feel that people begin to recognise as the calm channel, which can outcompete rumour threads when a case trends. Numbers need pictures sized to human experience. Joules and megatons are slippery. A measured voice pairs them with reach. Overpressure above 1 kilopascal within this oval. Window break risk near this line under clear skies. No crater-forming outcomes remain given current size bounds. Airburst altitude between 25 and 35 kilometers in the middle, 80% of cases. Maps are dangerous if they are too crisp. They look like promises. The fix is to show bands with labels, central likely conservative edge, and to annotate what would move the bands. People do better with ranges they can watch narrow than with a single thin line that will surely move. Timing language is another trap. Tomorrow means something different in Tokyo and Toronto. Measured voices use UTC or the audience's time zone and add day of week plus date. Thursday 1400 UTC, through 1600 Berlin, not tomorrow afternoon. They say how often the page updates and still post a note if nothing changed. That prevents stale screenshots from posing as breaking news and reduces the gap in which speculation grows. If an update is delayed, say so and say why. Weather closed a site, the object faded faster than forecast, or the pipeline reprocessed calibrations. Myths also grow from cognitive biases. We overestimate rare dramatic risks and underestimate common, dull ones. A measured voice doesn't scold, it leverages comparison. This object's current probability is smaller than your yearly chance of being hit by lightning by a factor of X. Background risk of all impacts of this size over the next Y years is Z. This object is below that. Framed carefully, these comparisons don't downplay, they contextualize. The goal is not to make people shrug, it is to make their mental yardstick match the real yardsticks. Technical words deserve patient unpacking. Non-gravitational acceleration sounds exotic until you say, sunlight warms ices, escaping gas acts like a very small thruster. Hyperbolic excess velocity becomes still moving fast even far from the sun. Covariance becomes our uncertainty bubble and which way it points. Good communication treats these as reusable building blocks. Once the audience learns a few bricks, they can follow most updates without new vocabulary. That is power against myths, which often rely on making the topic feel inaccessible. Another steady practice is showing your work without drowning people. A one-page What's Changed note, a link to machine-readable ephemerides for power users, and a canonical plot are enough for most days. If a journalist calls, offer quotes that carry numbers and verbs. Impact probability decreased by a factor of 10 after last night's observations from South Africa. The size range now favours 30 to 50 metres assuming a typical reflectivity. We see no coma, that keeps strength estimates in the rocky bin for modelling. These sentences are hard to misquote because their meaning lives in the numbers, not in adjectives. Rumour control works best when it is pre-authorised. Agree in advance who speaks on behalf of which institutions, which pages count as authoritative, and what the update cadence is. When a story runs ahead of facts, you can point to the pinned update and say, next scheduled numbers at 1800 UTC. This is not defensive, it is professional. It also gives local authorities something to reference if they are asked for comments, reducing the chance that a well-meaning official freelances with guesses. A common media arc is the quiet panic cycle: initial hype, community corrections, a combative headline about scientists backtracking, then silence. The measured answer is to make the middle visible from the start. Announce the uncertainty corridor, the expected shrink rate, the decision thresholds, and the likely end states on day one. When the end state is routine flyby, it feels like the plan, not a reversal. When rarely a case stays interesting, everyone already knows what the next rung on the ladder looks like. More telescopes, perhaps radar if geometry allows, tighter maps, and pre-written guidance if a narrow corridor persists. Finally, remember that curiosity is an ally. People click on space stories because they want to feel the sky is alive. A measured voice can feed that without feeding fear. Share the actual images, stacked frames where the mover is circled, the light curve wobbling as the object spins, the updated orbit plot with last night's points in a different colour. Praise the small observatories and classrooms that contribute a key data point along the line of variation. Explain why wide surveys and boring calibration work are heroic in their own way. When the public sees the craft behind the calm, myths have less oxygen, and the quiet truth becomes the interesting part. Most visitors are just that, visitors, and our job is to watch carefully, say exactly what we see, and show the plot again tomorrow with a little less fuzz than today. Perspective starts with time. Earth is 4.5 billion years old. Life has been here for most of that span. Complex animals for the last 500 million, humans for a blink. Across that timeline, change is constant and comes in different tempos. Some changes are slow and steady, continents drifting, climates cycling, species adapting. Others arrive as jolts, volcanoes, sudden climate flips, and a few times large impacts. Both tempos matter. Slow forces sculpt the stage, jolts rewrite parts of the script. When we talk about impact risk today, we sometimes mistake the jolt for the whole play. It is not. It is one kind of plot twist among many, rare on human scales, important on geological scales, and deeply interwoven with how life renews itself after loss. Mass extinctions are the headline events, but they're also infrequent. 5 big ones punctuate the fossil record, with many smaller pulses in between. The famous example is the End Cretaceous event 66 million years ago, where a large asteroid struck, climate shifted rapidly, and non-avian dinosaurs vanished alongside many other species. The aftermath was not an empty Earth, it was a rearranged one. Mammals diversified, birds radiated into niches that pterosaurs and others had held. Flowering plants flourished with new pollinators and herbivores. This pattern, shock, loss, then creative expansion, is not a justification for harm. It is an observation about resilience. Life is a network with redundancy and latent possibility. When a branch breaks, growth emerges along others that were once shaded. Other crises did not centre on impacts. The end Permian extinction, the most severe known, appears to have been driven by immense volcanism, greenhouse gas surges, ocean anoxia and cascading feedbacks. Icehouse hothouse swings, sea level changes, mountain building, and the slow drift of continents have all remade the biosphere in ways that produce both losses and bursts of innovation. In that broader gallery, asteroid impacts are a minority cause. They are dramatic and clean in the rock record, because a crater is a crisp signature, but their statistical role is one tile in a much larger mosaic. This matters for perspective. When we prepare for impacts today, we are addressing one rare hazard among many, not the sole threat to life or civilization. Scale is the bridge from geology to daily life. Tiny grains of dust constantly rain down unnoticed. Pebbles become meteors, bright and harmless. Meter-class entries make fireballs that end as high-altitude airbursts. Tens of meters objects can, if strong and steep, create shockwaves that break windows and rattle towns. These are rare on century timescales and are the main reason for simple advice like, if you see a bright daytime bolide, step away from windows and wait for the delayed boom. Larger impactors, hundreds of meters and up, are still rarer, with intervals long compared to recorded human history. Those are the sizes that motivate organised surveys and, in principle, space missions. Seeing this scale ladder helps regulate fear. It also clarifies responsibility. Small things are a public education and response topic. Medium things are a monitoring and civil protection topic. Big things are a monitoring and, with enough warning, a mission design topic. Each rung has tools sized to it. Evolutionary perspective avoids a trap, romanticizing catastrophe as the engine of progress. Innovations do not require disasters. They often emerge from sustained ecological interactions, predator-prey dynamics, arms races, symbioses, migrations, and environmental gradients. The Cambrian explosion's apparent rapidity, for instance, reflects thresholds crossed in oxygenation, developmental toolkits, and ecological complexity, not a single external shock. Catastrophes prune ordinary time events. When shocks do come, survivors tend to be generalists, small-bodied, widespread, or simply lucky in geography. That fact underlines a mundane truth about resilience at human scales. Diversity is a buffer. Diverse ecosystems bounce, monocultures snap. Diverse energy sources, supply chains, and information streams do the same for societies. Human perception adds another layer. We are pattern seekers with a bias toward vivid, sudden stories. A slow-moving curve of agricultural practice or conservation policy rarely grips attention like a sky flash, but risk lives in both shapes. The way through is to let awe and caution coexist. Awe keeps us invested in watching the sky and learning from it. Caution keeps us from overreacting to low-probability noise or underreacting to slow-moving certainties. Communication helps. If people know that most sky events are harmless and that rare harmful ones have simple, proportionate responses, they can carry awe without anxiety. Technology changes the equation in two directions. It increases our knowledge and our leverage. Wide-field surveys, fast pipelines, and space missions make us competent stewards against one category of rare shocks. It also increases our exposure to other risks of our own making: climate forcing, biodiversity loss, pollution, and brittle infrastructures. Perspective means not letting the glamour of cosmic threats distract from the mundane, chronic ones that are certain, ongoing, and entirely within our control. The atmospheric physics that turns most space rocks into light shows is not available for greenhouse gases, fisheries, soil, or misinformation. Focusing on those does not diminish the value of planetary defense. It frames it correctly as one slice of a broad responsibility to future people and other species. Ethics enters when we talk about interventions. If a deflection mission is ever needed, it will involve choices about who bears cost and risk, how decisions are made, and how transparent the process is. Even drills raise questions. Whose sky time gets reallocated? Which communities receive warnings that might affect local economies? How do we avoid crying wolf while staying candid about uncertainty? Perspective favours institutions that are boring in the best way. Open data, preset thresholds for action, rehearsed handoffs between scientific bodies and civil authorities, multilingual public notes posted on a schedule rather than pushed by hub or rumour cycles. When nothing happens, because probabilities fell as expected, standing down should feel like success, not like a story lost. Cultural memory helps. Many traditions carry sky lore, meteors as signs, comets as omens, that once reflected both wonder and fear. Today we can reinterpret that memory with gentleness. Meteors are reminders that space is active around us. Comets are repositories of early solar system chemistry. Interstellar objects are messages in bottles from other planetary workshops. Framing them this way keeps a place for meaning without borrowing dread. It also invites people into the craft of looking. Star parties with meteor counts, school projects that stack images to find movers, citizen science portals that let a classroom reduce an orbit's uncertainty by a measurable amount. Participation shrinks the gap between the public and the patient routines that actually keep us safe. Perspective also notices that rare is not the same as never. The responsible posture is layered readiness. For the smallest class, readiness is education, people knowing not to rush to windows during a bright daytime fireball. For the medium class, readiness is monitoring and clear corridors with practical guidance if needed. For the largest class, readiness is design work on the shelf, international agreements, and exercises that test both space and ground options. The goal is to keep each layer affordable and calm so that the existence of a plan does not require noise to justify itself. Preparedness that is light on its feet survives long quiet periods without becoming either complacent or theatrical. There is comfort in the deep statistics. Earth is not a target. It is a participant in a long, slow dance of orbits, where near misses are common and direct hits by large bodies are separated by spans longer than civilizations. Gravity's geometry, the atmosphere's physics, and our own surveillance all conspire to make most nights uneventful. The very fact that impacts loom large in imagination is a testament to how safe the daily world is compared to our stories. When something unusual does happen, it is almost always a learning event first, a hazard second. And learning compounds. Each case improves surveys, models, and communication the way careful maintenance improves a bridge. You rarely admire a safe bridge, you simply cross it, trusting the quiet work behind the scenes. At human scale, then, the balance message is steady. Life on Earth is robust and adaptive over long horizons. Impacts contribute to the long record of change but do not dominate it. On the timescales we inhabit, years and decades, impact hazards are mostly about measurement and clear words, not about drama. We can watch the sky with curiosity, invest lightly but consistently in early discovery, practice the few simple behaviours that matter for rare airbursts, and keep our bigger efforts aimed at the chronic certain pressures that shape our shared future. This is not indifference. It is proportionality. It lets wonder and responsibility sit at the same table, one eye on the stars, one hand on the work in front of us, and a calm confidence that both matter, each in their time. We come back to the everyday world the same way a telescope domes open at dusk and then close before dawn, slowly, with a handful of simple motions done in the same order each time. First, breathe in the idea that almost everything above us is peaceful background, a steady field of stars crossing the night the way clocks cross a kitchen wall. Breathe out the few moving points that earned our attention, the ones that survey cameras stitched into tracklets, that software linked into orbits, that people checked and rechecked until the fuzz became a path. Breathe in the comfort that physics is patient and repeatable. Breathe out the headlines that race because the sky does not rush for anyone. What remains is a small, clear routine. Look, measure, compare, explain that fits inside a human day and a human voice. The ground under your feet matters just as much as the sky overhead. So we translate numbers into ordinary habits. If you ever see a bright daylight fireball and feel the urge to watch, step away from windows, count to 10 and expect a delayed boom because sound travels more slowly than light. If you hear nothing and the streak fades, you just watch the atmosphere do its job. If you hear rumbles a minute later, that is the shockwave spending itself in air, not a sign of anything worse. Put that simple rule somewhere easy to find, as automatic as looking both ways before you cross a street. Most of the science in this story reduces to a handful of habits like that, sized for anyone, any age. When curiosity nudges, the tools to satisfy it are perfectly ordinary. Many observatories post nightly images and light curves. Public risk pages list orbits. probabilities and scales. Planetarium software and simple sky apps animate the paths of planets and show where meteor showers come from. Learning to read one orbital plot, one uncertainty ribbon, one pair of numbers on the Torino and Palermo scales is like learning your local bus map. Confusing once, then obvious forever. You do not need to memorize equations to grasp that ellipse means returning family, and hyperbola means passing guest, or that probability shrinks as nights stack up, or that no resonant return means the same visitor will not come back years later for a second try. The point is not to become an expert. It is to recognize the shape of a calm update when you see one. The human part of this system is a quiet relay race. Someone on a mountain in Hawaii or the Canary Islands scans a field and flags a mover. Someone in Chile, South Africa, or Australia picks it up a few hours later, adding dots to the arc. A graduate student learns to trust their centroid measurements. A veteran orbit fitter adjusts a model and posts revised ephemerides. An amateur with a modest telescope in the right longitude contributes a time-stamped point that squeezes the corridor by half. A larger facility squeezes in a short thermal pass that narrows size and reflectivity. None of this looks like a movie. It looks like shared spreadsheets, careful file names, and small emails that say nice catch and clouds here, trying again tomorrow. That ordinariness is the strength of it. If we zoom back to daily life, the same pattern holds. Small, steady acts build safety more reliably than dramatic gestures. The people who manage bridges do inspections no one applauds. The people who run weather radars post loops that most of us check only when rain threatens a picnic. The people who maintain vaccine cold chains do their job in warehouses at 3 a.m. Planetary defense, for all its cosmic tone, belongs to that family of work. It is a maintenance culture applied to orbits instead of steel beams, to probability plots instead of barometers. Seeing it that way shrinks it to a scale you already know how to trust. If you like rituals, there are gentle ones made for this subject. Step outside on a clear night, find a bright star, and hold your breath for a slow count of 5 while you notice how still it looks. Then pick a fainter star and count again. If a meteor sketches a line anywhere in your vision, let it be a reminder that atmosphere is working all the time, turning small stones into brief light and nothing else. Indoors, once in a while, open one of the public dashboards and read the first line for the newest object. Designation, observing arc, size range, current risk scale. If it says 0, nod and close the tab. If it says 1, know that it is a normal discovery and will almost certainly slip to 0 with a couple more nights. If anything truly unusual ever happens, that page will not whisper. It will speak plainly about what is known and what to do. A soft landing also means proportion. The same attention that helps us separate possibility from probability in the sky helps us separate spectacle from substance on the ground. It keeps us from neglecting slow, certain work, like reducing emissions, restoring habitats, and strengthening public health, just because a fast, rare story is more exciting. The gift of learning the sky's calm rhythms is that you can carry them into other topics. You start asking, what is the baseline? What does background risk look like? Which small, repeated actions move the dial? What would a simple, useful public message sound like if I had to write it? That kind of attention is contagious and quietly civic. There is room for wonder without worry. Comets are time capsules of early chemistry. Meteor showers are scheduled poetry arriving when Earth crosses old dust trails. An interstellar visitor is a postcard from a different neighborhood saying only, "I was here." And that is enough. If a telescope image looks like a smudge with a caption full of numbers, it is still art. Art made by light that left a cold stone far away and ended its journey on a sensor warmed by human hands. You are allowed to enjoy that for its own sake. Wonder is not the same as alarm. It is the opposite. Attention that asks for nothing in return. For the practical-minded, it helps to see how the parts connect. Wide surveys reduce the unknowns pool. Follow-up observations turn maybes into knowns. Orbit models draw map lines with little grey belts that shrink. Entry models translate sizes and speeds into altitudes and safe, simple advice. Communication practices keep each update the same shape so differences jump out. Education turns a handful of phrases, airburst, overpressure, MOID, non-gravitational push, into household words that strip away mystery. Policy puts thresholds on paper so decisions aren't made in the heat. Altogether, this feels less like a drama and more like plumbing. Hidden most days, essential when needed, quietly improving with each repair. If you want to contribute, the on-ramps are friendly. Citizen science platforms let you help spot movers in survey images. Local astronomy clubs share equipment and sky time and teach safe observing. Teachers turn orbital plots into math exercises that feel like puzzles instead of chores. Even a short note you share with friends, if you see a daylight fireball, step back from windows and wait for the boo, is a contribution. It replaces rumour ladders with a single useful rung. Participation is how a topic stops being someone else's and becomes ours. If your interest is gentler still, just a wish for better sleep, let the sky's statistics help you. Large impacts are rare on human timescales. The atmosphere is an automatic brake that does not need our permission to work. Surveys run every clear night that domes can open. Risk pages tend to be full of zeros, and when a number twitches up, the most likely next number is lower. The system is designed to say out loud when it has a news, and designed to say just as clearly when it does not. That means you do not need to check every rumour. You can check the places that speak in the same measured format every time, then put the topic down and get on with your day. We can walk through the world with both feet in ordinary shoes and both eyes open to the sky. Morning routines still fit. Make coffee or tea, skim a headline, skim right past the ones that use could without a number, and give a small nod to the invisible work of telescopes sleeping in daylight after a night of looking. Evening still fits. Porch light off, one glance upward, maybe a meteor, maybe not. The same calm air doing the same ancient job. Between those two bookends, we do what people always do. Maintain the things we rely on, keep our promises to each other, and tell the truth simply enough that everyone can carry it. That is the softest landing there is. The sense that the sky above is interesting, the ground below is solid, and our part is not to hold the heavens up but to understand them well enough that we can breathe in and breathe out with a little more ease. If you made it this far, thank you for letting your mind wander with me tonight. We sifted through worries and what-ifs and found the steady ground beneath them. Clear measurements, calm plans, and a sky that is mostly quiet. If that gave you a little more room to breathe, consider tapping subscribe and the bell so you can join me next time we turn complicated space stuff into simple, sleepy sense. A quick like or a comment with your favourite moment helps more than you'd think, and if there was a line that eased your mind, share it with someone who could use a gentler night. Before you drift off, notice the way your body softens when the story slows down. Shoulders loosen, jaw unclenches, the space behind your eyes clears a bit. The sky above is vast and patient. You don't have to hold it up. Breathe in slowly to a count of 4, hold for 2, and let the air slip out for 6. Again, let your thoughts stack like quiet frames from a telescope. No rush, no effort, just the next small picture arriving when it's ready. All the numbers and models can wait. The world will still be here in the morning, and the people who keep watch will keep watch while you rest. If you're still awake and want more and more, there's a playlist waiting at the end that gathers calm journeys, cosmic, oceanic, historical, made to end in soft silence. Tell me in the comments what topic you'd like to explore in the same gentle way. More interstellar visitors, soothing deep-sea science, sleepy philosophy, or something entirely different. Your ideas shape what we make here. This channel is a collaboration between your curiosity and my promise to keep things clear, kind, and unhurried. If you arrived worried and you're leaving lighter, that's enough for tonight. Set your phone face down, let the room grow dim, and let the last few sentences blur into the hush between breaths. The sky has been practicing calm for billions of years. You get to borrow some of that now. Thank you for watching, for resting, for being here. Be well, sleep deeply, and I'll see you in the next gentle chapter. Good night.